Hello there, and welcome to Science for Sleep, a place where curiosity slows its pace, where questions are allowed to linger, and where science doesn't rush you toward answers, but walks beside you instead. Wherever you are listening from tonight, whether the room around you is already dark or softly lit, whether the day has just ended or is still echoing in your thoughts, I'm glad you're here. Take a moment to notice how still everything can feel when you stop expecting something to happen. That feeling will serve us well tonight. Before we drift any further, I'll ask gently, without urgency. Where are you listening from right now? A bedroom, a couch, a long drive, or a quiet corner where the world finally stopped asking things of you? And if you happen to know what time is it where you are, it's always a fitting question here, because even when we're talking about the largest ideas the universe has to offer, we're still experiencing them one moment at a time. If you find this space calming, interesting, or simply a good companion as you wind down, you're very welcome to like the video or subscribe. It helps this slow, thoughtful corner of science reach others who might need a softer ending to their day. No pressure at all. Now, let's settle in. Tonight, we're going to spend some time with something that sounds dramatic, even ominous, but is surprisingly quiet in how it works. Dark energy. The name alone feels heavy, as if it should come with shadows, warnings, or science fiction sound effects. Yet the reality is far stranger, and far calmer than the name suggests. Dark energy does not roar. It doesn't crash galaxies together or tear holes in space without warning. In fact, it does almost nothing at all on small scales. You can sit safely in your chair, breathe slowly, and know that dark energy is not pulling at you in any noticeable way. And yet, on the largest scales imaginable, on distances so vast that numbers start to lose their meaning, dark energy is shaping the future of everything. To ease into this, imagine the universe not as something explosive or chaotic, but as something patient. Picture galaxies drifting apart slowly, like leaves on a wide, calm lake. For a long time, scientists believed that gravity would eventually slow this drifting. After all, gravity pulls things together. That's what it does best. Toss a ball upward, and it comes back down. Build a star, and gravity keeps it together. Gather enough matter, and gravity builds galaxies, clusters, and cosmic structures that last billions of years. So it seemed reasonable to assume that the universe, after its hot and dense beginning, would gradually slow its expansion. Maybe it would coast. Maybe it would eventually stop. Some even imagined it might reverse direction and begin to collapse back inward. These were all calm, orderly expectations. Nothing too strange. Dark energy entered the story quietly, almost politely, by telling us that all of those expectations were wrong. What makes this especially unsettling and fascinating is that dark energy wasn't discovered because someone went looking for it. No telescope was pointed at the sky with the intention of finding a mysterious force pushing the universe apart. Instead, dark energy appeared as an explanation of last resort, something scientists arrived at only after the universe refused to behave the way it was supposed to. That's often how the deepest discoveries happen. Not with a grand announcement, but with a persistent mismatch between expectation and reality. To understand why dark energy is so unsettling, it helps to notice how little of the universe it actually interacts with in any direct way. It doesn't clump, it doesn't gather, it doesn't form stars, planets, or anything you could point to and say, there it is. You won't find a dark energy particle. You won't trap it in a detector. You won't feel it pass through you. And yet, by every measurement we have, dark energy makes up most of the universe. Not most of what we can see. Not most of the things we can touch or measure in a laboratory. Most of everything. Galaxies, stars, gas, dust, planets, black holes, all of that combined is only a small fraction of what exists. Even dark matter, which already feels elusive and invisible, accounts for less than dark energy does. This is where the feeling of scale begins to shift. Dark energy doesn't matter in your kitchen, your city, or even within your galaxy. Gravity overwhelms it completely at those scales. But stretch your view far enough, beyond clusters of galaxies, beyond filaments and voids, beyond anything that feels familiar, and dark energy begins to dominate. It becomes the quiet rule governing how space itself behaves. One way to think about it, without leaning into metaphor too heavily, is to imagine space as something active rather than empty. We tend to think of space as nothing, a backdrop where things happen. But modern physics has taught us that space has properties. It can stretch, it can curve, it can expand. And dark energy appears to be tied not to matter, but to space itself. This is part of why it's so difficult to describe in simple terms. We're used to forces acting on objects, push this, pull that. Dark energy doesn't behave that way. It doesn't push galaxies through space so much as encourage space itself to grow between them. That distinction matters. When astronomers observe distant galaxies, they aren't seeing them fly through space like sparks from a fire. Instead, they're seeing the distance between galaxies increase because the space in between is expanding. Dark energy seems to accelerate that expansion, not by acting locally, but by influencing the large-scale behavior of the universe as a whole. If that feels abstract, don't worry. It's not a failure to understand. It's a reflection of how unfamiliar the idea truly is. For most of human history, the universe was something static and eternal. Stars wheeled overhead. Seasons passed. The sky felt permanent. Even when scientists began to understand gravity and motion, the universe itself was often assumed to be steady and unchanging on the larger scales. The idea that space could expand at all was once controversial. Now we're faced with something even stranger. Space isn't just expanding, it's doing so faster over time. This acceleration is where dark energy makes itself known. The word acceleration carries baggage. We associate it with engines, thrust, effort. But cosmic acceleration doesn't require fuel in the usual sense. There is no cosmic engine revving louder as time goes on. Instead, dark energy appears to be a constant feature of space, something that becomes more important as the universe grows larger and emptier. That last part is key. As the universe expands, matter becomes more spread out. Gravity weakens over vast distances. Dark energy, on the other hand, does not thin out in the same way. Its influence remains, and over time, it begins to dominate the cosmic balance. This leads to a quiet but profound shift. Early in the universe's history, gravity was in charge. Matter was dense, structures formed, galaxies assembled, stars ignited. Over billions of years, gravity built the universe we see today. But as expansion continued, the scales tipped. Dark energy, once negligible, slowly took over. What's especially strange is that dark energy doesn't seem to change much as the universe expands. It doesn't dilute like matter or radiation. If anything, its influence becomes more apparent as everything else spreads out. This is one of the reasons scientists suspect dark energy might be tied to the vacuum of space itself. Empty space, it turns out, may not be empty at all. This idea is not new. In fact, it has roots going back more than a century, to a time when physicists were first grappling with how gravity and space might interact. At one point, an additional term was introduced into the equations describing the universe, a term meant to hold the cosmos still, to counteract gravity and prevent collapse. That term was later discarded when expansion was discovered, and for decades it was treated as an embarrassing mistake. Then, unexpectedly, it came back. Dark energy may be connected to that same idea, though not in a simple or fully understood way. What once seemed like an error now looks uncannily relevant. It's one of those moments in science where an old assumption quietly waits for the universe to catch up. Despite decades of observation, we still don't know what dark energy actually is. We know what it does. We know how it affects expansion. We can measure its influence through the motion of distant galaxies and the structure of the universe on the larger scales. But its nature remains unclear. Is it a property of space? Is it a field that fills the universe? Is it truly constant, or does it change slowly over time? These questions remain open, and they're not easy ones. What we do know is that dark energy is remarkably uniform. No matter where we look, its effects appear the same. This uniformity suggests that dark energy is woven into the fabric of the universe itself, rather than being tied to specific regions or objects. That idea can feel unsettling, but it can also feel oddly calming. There is something steady about dark energy, something persistent. It doesn't flicker or fluctuate in dramatic ways. It doesn't form storms or eruptions. It simply is. As you rest here, listening, it may help to notice the contrast. On human scales, life is full of change, urgency, and motion. On cosmic scales, the most powerful influence shaping the future of everything is slow, even gentle. Dark energy does its work over billions of years, stretching space so gradually that no single moment feels different from the last. And yet, added together, those moments reshape the universe. This is the tone dark energy sets. Not chaos, but patience. Not destruction, but distance. Galaxies drifting farther apart, light travelling longer paths, the universe becoming quieter and more spacious over time. For now, it's enough to let the question settle. What is dark energy really? Not as a dramatic force, but as a subtle presence shaping the larger story there is. For a long time, the universe appeared to be behaving exactly as expected. Galaxies were moving away from one another, yes, but that wasn't surprising. The idea of an expanding universe had already settled into the scientific imagination by the mid-20th century. What mattered wasn't that expansion existed, but how it behaved over time. Most astronomers assumed it should be slowing down. Gravity, after all, pulls, it gathers, it resists separation. Given enough matter spread across space, gravity should gradually act as a brake on cosmic expansion. That assumption felt so reasonable that few questioned it deeply. The real debate wasn't whether expansion was slowing, but by how much. Some models predicted a universe that would eventually stop expanding and coast at a constant size. Others suggested it might reverse direction and collapse back inward. Still others imagined a delicate balance, expansion slowing forever, but never quite stopping. These were differences of detail, not of principle. The principle itself felt secure. And that is what made the discovery so strange. It didn't arrive with a single dramatic observation or a sudden announcement that rewrote everything overnight. Instead, it emerged from a careful, methodical attempt to answer what seemed like a fairly straightforward question. How fast is the universe expanding, and how has that rate changed over time? To answer that, astronomers needed a way to measure enormous distances across the cosmos, not approximate distances, not relative ones. Actual calibrated measurements that could tell them how far away a galaxy really was. That's harder than it sounds because space does not come with built-in markers. There are no cosmic mileposts, no universal rulers stretching between galaxies. So astronomers rely on what are called standard candles, objects whose intrinsic brightness is known well enough that, by comparing how bright they appear from Earth, you can calculate how far away they are. If you know how bright something truly is, and you see how faint it looks, distance follows from basic physics. One of the most reliable standard candles ever discovered is a particular type of stellar explosion known as a Type Ia supernova. These events occur when a white dwarf star accumulates too much mass from a companion and undergoes a catastrophic thermonuclear explosion. What makes them special is their consistency. They reach nearly the same peak brightness every time, making them excellent cosmic distance markers. By the 1990s, astronomers had grown confident enough in their understanding of these supernovae to use them as tools for mapping the expansion history of the universe. Two independent research teams set out to do exactly that. Their goal was not to uncover a cosmic mystery. Their goal was to measure deceleration. They expected to find that distant supernovae appeared brighter than they would in a steadily expanding universe. Brighter would mean closer. Closer would mean that expansion was slowing over time just as gravity should dictate. What they found instead was the opposite. The distant supernova were dimmer than expected. Not by a little. Enough to raise eyebrows. Enough to trigger rechecks. Enough to prompt long discussions late into the night. Dimmer meant farther away. Farther away meant the universe had expanded more than expected during the time the light had been travelling toward us. In other words, expansion was not slowing down. It was speeding up. At first, this result was treated with suspicion. That reaction wasn't denial so much as caution. Extraordinary claims require extraordinary confidence, and astronomers are trained to mistrust results that contradict well-established expectations. Every possible source of error had to be examined. Could the supernovae be intrinsically dimmer in the distant past? Could dust be absorbing their light? Could selection effects be skewing the sample? Could the calibration be off? Could there be unknown variations in these explosions that hadn't yet been accounted for? Months turned into years of scrutiny. Both teams cross-checked their data independently. Methods improved. More supernovae were observed. Different telescopes, different analysis techniques, different assumptions. And yet, the result held. The universe was accelerating. This was not just surprising. It was deeply uncomfortable. Acceleration implied a cause. Something had to be driving this behaviour. Something had to be counteracting gravity on the largest scales and then overpowering it. But nothing in existing cosmological models could do that. There was no known form of matter or radiation that behaved this way. The equations describing the universe could accommodate acceleration, but only by introducing something new. A term that behaved very differently from ordinary matter. Something with a strange pressure. Something that acted not by clumping, but by spreading. That something became known as dark energy. The name itself was a placeholder, not an explanation. Dark in this context didn't mean evil or mysterious in a dramatic sense. It meant unknown and invisible, much like dark matter before it. Energy, because whatever this was, it influenced the dynamics of the universe. What made this discovery especially unsettling was how late it came. Humans had been studying the cosmos scientifically for centuries. We had mapped planetary motions, deciphered stellar spectra, measured cosmic background radiation, and constructed detailed models of how the universe evolved. And yet, we had somehow missed the dominant component of the cosmos until the very end of the 20th century. It wasn't hiding because it was weak. It was hiding because its effects only reveal themselves across enormous distances and long stretches of time. Dark energy does almost nothing locally. Within galaxies, gravity wins. Within clusters of galaxies, gravity still wins. Even between neighbouring clusters, gravity can dominate. Only when you average over the largest scales does dark energy emerge as the primary influence. That scale dependence is part of what makes it so unintuitive. We're used to forces acting everywhere. Gravity pulls whether you're near or far. Electricity pushes whether the distance is small or large, though it weakens. Dark energy doesn't behave that way. Its influence is cumulative, not concentrated. The farther apart things already are, the more room there is for dark energy to matter. This leads to a subtle but profound realization. Dark energy did not suddenly switch on at some moment in cosmic history. It was always there, quietly present. But for billions of years it was overshadowed by matter and radiation. Only as the universe expanded and matter spread out did dark energy step into the foreground. In hindsight, this explains why earlier observations didn't reveal it. The universe simply wasn't old or large enough yet for dark energy to dominate. The discovery came when it did because that's when it became observable. Still, knowing when something becomes visible does not explain what it is. In the immediate aftermath of the discovery, cosmologists scrambled to adjust their models. The simplest explanation was to revive an old idea that had been sitting in the equations for decades. largely ignored. A constant energy associated with space itself. This term had been introduced earlier in the history of cosmology for a completely different reason. At the time, the universe was believed to be static. Gravity alone would cause it to collapse, so an additional repulsive term was added to balance it out. Once expansion was discovered, that term seemed unnecessary and was set aside. Now it was back, but in a new role. Instead of holding the universe still, it was driving it apart. What made this explanation appealing was its simplicity. A constant energy density filling space would naturally cause accelerated expansion. As space grows, the total amount of this energy increases because there is more space for it to inhabit. That growth leads to acceleration, not slowdown. This idea fit the data remarkably well. Too well, some might say. But fitting the data is not the same as understanding the cause. While the equations worked, the physical meaning remained elusive. Why should empty space have energy? Why should that energy have the particular value required to match observations? Why should it dominate now rather than earlier or later? These questions remain open. Another unsettling aspect of the discovery was how it forced a re-evaluation of cosmic fate. Before dark energy, the long-term future of the universe depended primarily on how much matter it contained. Enough matter would eventually halt expansion. Too little would allow it to expand forever, but ever more slowly. Dark energy changed that picture entirely. If acceleration continues, galaxies will drift farther and farther apart. Over unimaginably long timescales, distant galaxies will slip beyond the observable horizon. Their light will never reach us again. The universe will appear emptier, quieter, darker. This is not destruction in a violent sense. It is separation, distance increasing, isolation growing. When the discovery was announced, it was met with a mix of excitement and unease. Excitement, because it opened an entirely new field of inquiry. Unease, because it suggested that most of the universe was governed by something we barely understood. Yet, in a strange way, the discovery was also reassuring. It confirmed that the universe still had the capacity to surprise us, that despite our equations and models, reality retained a stubborn independence. It also demonstrated the power of careful observation. No new particle detector was required. No exotic experiment was built. The discovery came from patiently measuring light that had travelled for billions of years and noticing that it didn't behave quite as expected. There is something quietly humbling about that. As more observations accumulated, confidence grew. Measurements of the cosmic microwave background, the large-scale distribution of galaxies, and gravitational lensing all pointed toward the same conclusion. A universe dominated by dark energy, with a smaller contribution from dark matter and an even smaller one from ordinary matter. The cosmic inventory shifted. Stars, planets, gas and dust, the things we instinctively think of as the universe, were revealed to be a minor ingredient. The universe was not mostly stuff. It was mostly something else. This realization can feel disorienting, but it also reframes our place in a calmer way. The universe does not revolve around what we can see or touch. It operates according to principles that don't prioritize familiarity. Dark energy did not arrive to complicate things unnecessarily. It arrived because the universe demanded it. And yet, for all the upheaval this discovery caused, daily life went on unchanged. The sky did not look different. Stars did not flicker strangely. Gravity still held planets in their orbits. Dark energy does not announce itself in obvious ways. Its influence is subtle, cumulative, patient. The story of dark energy is not one of sudden revelation followed by neat explanation. It is an ongoing adjustment, a slow reshaping of how we think about space, time, and the structure of reality. For most of the 20th century, the behaviour of the universe seemed, at least in broad outline, reassuringly sensible. Once astronomers accepted that space itself was expanding, It felt natural to assume that this expansion would gradually lose momentum. The universe, after all, contains matter. Matter has mass. Mass produces gravity, and gravity pulls things together. Put those ingredients into a cosmic setting, and slowdown feels inevitable. This expectation wasn't casual or vague. It was woven deeply into the mathematical descriptions of the universe and reinforced by everyday intuition. Throw a ball upward and it slows, stops and falls back down. Fire a rocket without continuous thrust and it coasts, then drifts. Expansion without resistance is not how we expect the physical world to behave. So when scientists spoke about the universe expanding, they did not imagine it doing so freely forever. They imagined it like a stone tossed into the air at the moment of the Big Bang, initially fast, then steadily decelerating under the pull of its own gravity. That picture shaped decades of cosmological thinking. The central question was never whether expansion was slowing, but how much matter existed to slow it down. Gravity was the known quantity. Matter was measurable, at least in principle. If you could count everything in the universe, all the galaxies, gas, dust, radiation, and unseen mass inferred from gravitational effects, you could calculate the future. This gave rise to a set of elegant possibilities. If the universe contained enough matter, gravity would eventually halt expansion entirely. After reaching a maximum size, the universe would reverse direction and begin to contract. This scenario was often called a closed universe. Expansion would give way to collapse, perhaps ending in a dense, hot finale. If the universe contained too little matter, expansion would continue forever, but it would slow over time, approaching a gentle crawl. Galaxies would keep drifting apart, but ever more sluggishly. This was the open universe scenario, and between these two extremes lay a delicate balance. A universe with just the right amount of matter would expand forever, slowing continuously, but never quite stopping. This was known as the flat universe, not because it lacked shape in the everyday sense, but because its geometry was balanced precisely between open and closed. These scenarios were clean, logical, and grounded in gravity behaving the way gravity always had. Importantly, none of them included acceleration. Acceleration would have implied that something was actively pushing the universe apart, not just allowing it to coast. That idea felt unnecessary at best and unmotivated at worst. There was no known physical mechanism to justify it, and no observational reason to invoke it. So cosmologists focused their efforts elsewhere. They worked to measure how much matter existed. They refined models of galaxy formation. They studied the afterglow of the early universe. They debated geometry, curvature, and density, all within a framework where gravity ruled unchallenged. Even the language used at the time reflected this confidence. Scientists spoke of deceleration parameters, values meant to quantify how strongly gravity was slowing expansion. The universe slowing down was not a hypothesis, it was an assumption. To appreciate how deeply this assumption ran, it helps to remember that gravity had never failed to slow anything down on large scales. Planets slow in their orbits without continuous input. Stars form because gravity overcomes expansion locally. Galaxies cluster because gravity pulls them together over millions of years. Why should the universe be any different? There was also an aesthetic preference at play, though scientists rarely admit this openly. A universe governed by gravity alone felt elegant. One force-shaping structure, motion, and fate. No need for extra ingredients, no mysterious pressures or unseen energies influencing the outcome. Simplicity carries weight in theoretical physics. All else being equal, simpler explanations are preferred, and for a long time, gravity alone seemed sufficient. This confidence was reinforced by early observations. When astronomers first measured the redshifts of distant galaxies, they found exactly what expansion predicted. The farther away a galaxy was, the faster it appeared to be receding. This relationship became a cornerstone of cosmology. But those early measurements were limited. They could tell astronomers that expansion existed and roughly how fast it was happening now. They could not easily reveal how expansion had changed over billions of years. For that, scientists needed much deeper observations, looking farther back in time. Light takes time to travel. When we observe distant galaxies, we see them as they were long ago. This makes astronomy a form of time travel. By comparing nearby galaxies, seen as they are now, with distant ones, seen as they were billions of years ago, astronomers can reconstruct the history of cosmic expansion. For a long while, the available data simply wasn't precise enough to challenge existing assumptions. Measurements had large uncertainties. Different models fit equally well, and since no one expected acceleration, no one went looking for it explicitly. This is an important point. Science does not always advance by asking open-ended questions. Often it advances by refining answers to questions we think we already understand. In this case, the question was not, is the universe accelerating, but how fast is it slowing down? That framing shaped experimental design, data analysis and interpretation. When researchers set out to measure distant supernovae, they did so expecting to quantify deceleration. Their tools were calibrated for that purpose. Their mental models were aligned with it. Acceleration was not part of the plan. This is not a flaw in the scientific process. It is how understanding progresses. Assumptions are necessary. They allow questions to be asked at all. What matters is whether those assumptions can be challenged by evidence, and eventually they were. But before that challenge emerged, cosmologists spent years refining the gravitational picture. They improved measurements of cosmic density. They accounted for dark matter, which added gravitational pull without emitting light. Dark matter strengthened the expectation of slowdown. More mass meant more gravity, more resistance to expansion. Even with dark matter included, however, the numbers were uncertain. Some measurements suggested a universe close to flat. Others leaned toward open, but none suggested that expansion should speed up. Gravity, after all, only attracts. This made the eventual discovery of acceleration feel almost like a violation of common sense, not because it contradicted a single theory, but because it contradicted a deeply ingrained pattern of thinking. The universe was supposed to behave like a ball thrown upward. Instead, it behaved like a ball that somehow picked up speed as it climbed. At first glance, this seems absurd, but the universe does not owe us intuitive behavior. One subtle reason acceleration was so hard to anticipate lies in how gravity works in general relativity. In everyday terms, gravity is associated with attraction, but in Einstein's theory, gravity is not just about mass. It is about energy, pressure, and the geometry of space-time itself. Most forms of energy, including matter and radiation, contribute to gravitational attraction. They curve space-time in ways that pull things together. But general relativity allows for more exotic possibilities. Under certain conditions, energy can produce repulsive gravitational effects. These possibilities were known mathematically, but they were not taken seriously as physical realities. They seemed artificial, something that existed on paper but not in nature. So when cosmologists thought about the universe slowing down, they were not ignoring general relativity. They were applying it in the most straightforward way, assuming the dominant energy components behaved normally. That assumption held until observations demanded otherwise. Looking back, it's clear that the expectation of slowdown was not naive. It was reasonable, well-supported, and consistent with everything known at the time. The surprise was not that scientists believed the universe was decelerating. The surprise was that it wasn't. This moment marked a quiet turning point in cosmology. The question shifted from measuring deceleration to explaining acceleration. The burden of explanation moved from refining known quantities to introducing something fundamentally new. Dark energy did not emerge because scientists wanted it. It emerged because gravity alone could no longer account for what was observed. That transition is worth sitting with for a moment. It highlights a key feature of scientific progress. When reality refuses to cooperate with expectation, expectation must yield. No matter how comfortable or elegant a theory may be, it is always provisional. The universe does not simplify itself for our convenience. As measurements improved and confidence in acceleration grew, the old slowdown scenarios began to fade. Closed, open, and flat universes were reinterpreted in a new context. Geometry alone was no longer enough to determine fate. The behavior of dark energy now played a central role. A universe could be geometrically flat and still expand forever at an accelerating rate. Density was no longer destiny. This reframing had profound consequences. It meant that knowing how much matter exists is not sufficient to predict the future. One must also understand the properties of dark energy, something far more elusive. It also meant that the early universe and the late universe are governed by different dominant influences. Gravity shaped the early cosmos. Dark energy shapes the future. That division introduces a kind of asymmetry into cosmic history. The rules did not change, but their balance did. The universe evolved into a state where a previously negligible component became decisive. This raises deeper questions. What exactly is this component? Why does it behave the way it does? And why did it become important when it did? When something cannot be seen, touched, or isolated in an experiment, the natural reaction is to doubt its existence. Human intuition is built around direct experience. We trust what resists our hands, reflects light into our eyes, or leaves some obvious trace behind. Dark energy offers none of that. It does not glow. It does not clump. It does not collide. It does not announce itself with sparks, sounds, or sudden changes in the sky. And yet, its presence is inferred with increasing confidence, not through a single observation, but through a pattern that repeats no matter where we look. This is one of the quiet tensions at the heart of modern cosmology. We are deeply certain that dark energy affects the universe, while remaining unsure about what it actually is. That certainty does not come from faith or speculation. It comes from measurement. Careful, layered, often indirect measurement, repeated in different ways by different instruments, all pointing toward the same conclusion. Understanding how something invisible can be measured requires stepping away from the idea that measurement always means direct detection. In science, many things are known by their effects rather than their appearance. Gravity itself was understood long before anyone could describe it mathematically. No one has ever seen gravity. We infer it from falling objects, orbiting planets, and bending trajectories. Dark energy operates in a similar way, though on scales so large that the human mind struggles to keep them in view. The first thing to clarify is that dark energy is not measured in a laboratory. There is no detector waiting for dark energy particles to pass through it. Instead, dark energy is measured through its influence on the expansion history of the universe. It reveals itself in how distances between distant objects change over time. That may sound vague, but the methods involved are precise. Astronomers measure distances in the universe using multiple independent techniques. Each has its strengths and limitations. What matters is not that any single method points toward dark energy, but that many of them do, in agreement with one another. One of the most important measurements comes from observing distant supernovae, as discussed earlier. These stellar explosions act as calibrated beacons. By comparing how bright they appear to how bright they are known to be, astronomers determine their distance. By comparing that distance to how much their light has been stretched, or redshifted, they infer how fast the universe was expanding when that light was emitted. When these measurements are plotted across billions of years, they reveal a pattern. Expansion slowed early on, as expected under gravity's influence. Then, at a certain point, it stopped slowing and began to speed up. This transition is not guessed. It is reconstructed from data points spread across cosmic time, but supernovae are not the only line of evidence. Another comes from the cosmic microwave background, the faint afterglow of the early universe. This radiation fills space uniformly and carries with it a detailed record of conditions when the universe was only about 380,000 years old. tiny temperature variations in this background encode information about the universe's geometry, composition, and expansion history. When scientists analyze this radiation, they find that the universe is very close to geometrically flat. In a universe governed only by matter and radiation, that flatness would require a precise balance that is difficult to maintain over billions of years. Dark energy helps explain why the universe appears flat today, even after such a long expansion. The cosmic microwave background does not measure dark energy directly. Instead, it constrains how much dark energy must exist to make the rest of the observations consistent. Large-scale structure provides another window. Galaxies are not distributed randomly. They form clusters, filaments, and vast empty regions known as voids. The way these structures formed and evolved depends on how fast the universe expanded over time. Faster expansion suppresses the growth of large structures by pulling matter apart before gravity can fully gather it. By mapping the distribution of galaxies across enormous volumes of space, astronomers can infer how expansion influenced structure formation. The observed patterns match a universe where dark energy plays a dominant role at late times. There is also gravitational lensing, the bending of light by massive objects. When light from distant galaxies passes near large concentrations of matter, its path is slightly distorted. By measuring these distortions statistically across many galaxies, scientists can map the distribution of matter and infer how structure has evolved. Again, the results are consistent with accelerated expansion driven by dark energy. What makes this especially compelling is that these methods are largely independent. They rely on different physics, different instruments, and different assumptions, yet they converge on the same basic picture. This convergence is what turns an invisible influence into a measurable one. Dark energy is not measured by touching it. It is measured by accounting for everything else, and noticing what must be added to make the universe behave the way it does. In a sense, dark energy is what remains when all known contributions are subtracted and the equations still do not balance. This kind of inference is not unusual in science. Neptune was discovered not by direct observation, but by noticing irregularities in Uranus's orbit. The neutrino was proposed to account for missing energy in particle decays long before it was detected. Dark matter itself was inferred from galaxy rotation curves decades before any attempt at direct detection. Dark energy belongs to this family of discoveries. Its presence is demanded by consistency. Still, measuring dark energy is not the same as understanding it. The measurements tell us how much of it there appears to be, and how it behaves on average. They do not tell us why it exists or what fundamental process gives rise to it. What we can say with confidence is that dark energy behaves as if it has negative pressure. Pressure is not something we usually associate with cosmic forces, but in general relativity, pressure contributes to gravity just as energy density does. Positive pressure adds to gravitational attraction. Negative pressure does the opposite. It produces a repulsive effect. This does not mean dark energy is pushing galaxies like a compressed spring. It means that when its properties are inserted into the equations describing space-time, the result is accelerated expansion. The idea of negative pressure sounds strange, but it is not entirely alien. In everyday physics, tension in a stretched object can be thought of as negative pressure. Pull on both ends of a rubber band and it resists being compressed. Dark energy behaves as if space itself resists being pulled back together. This resistance becomes more important as the universe grows. Another way to describe what is measured is through an equation of state, a relationship between pressure and energy density. For ordinary matter, pressure is small compared to energy density. For radiation, pressure is positive and significant. For dark energy, measurements suggest that pressure is negative and nearly equal in magnitude to energy density. This specific relationship produces acceleration. Current observations are consistent with dark energy, behaving like a constant energy density filling space uniformly. This is often referred to as a cosmological constant. In this simplest model, The amount of dark energy per unit volume does not change as the universe expands. That constancy has measurable consequences. It predicts a specific expansion history. It predicts how structures grow. It predicts how distances relate to redshifts. So far, observations agree remarkably well with this picture. But agreement does not equal certainty. Scientists continue to test whether dark energy truly behaves as a constant, or whether it might evolve slowly over time. Even small deviations from constancy could hint at a deeper explanation. To search for such deviations, astronomers conduct ever more precise surveys. They map millions of galaxies. They measure subtle distortions in light. They track the expansion rate at different epochs. Each improvement tightens the constraints. So far, dark energy remains stubbornly simple in its behaviour, even as it remains mysterious in origin. This simplicity is itself puzzling. When physicists attempt to calculate the energy of empty space using quantum field theory, they arrive at a value that is wildly different from what is observed. The predicted energy density is larger by an enormous factor. Reconciling this discrepancy is one of the greatest unsolved problems in theoretical physics. Yet observationally, dark energy appears calm, uniform, and consistent. This tension between theory and measurement is not a sign of failure. It is a sign that something fundamental is missing from our understanding. What matters for now is that dark energy is not a speculative add-on. It is not a placeholder awaiting confirmation. It is a measured component of the universe, supported by multiple lines of evidence. We cannot point to it, but we can point to its consequences. We can measure how fast galaxies recede at different distances. We can measure how structure grows. We can measure how space has expanded over time. And from these measurements we infer the presence of something that behaves unlike any familiar form of matter or energy. That inference is not fragile. It does not rest on a single assumption. It is reinforced every time new data arrives and fits the same framework. Still, the discomfort remains. Measuring something you cannot see requires a shift in mindset. It requires trusting patterns over appearances. It requires accepting that the universe does not prioritize what is easy to observe. As listeners resting here with these ideas, there is no obligation to resolve that discomfort. It is enough to notice it. Science often advances by sitting with uncertainty rather than rushing to eliminate it. Dark energy invites that patience. It reminds us that the universe can be governed by influences that leave no direct trace, only a gradual reshaping of the largest structures that exist. It teaches us that measurement does not always mean capture, and that understanding often begins with noticing what does not fit. Expansion is a word that sounds simple until you try to picture what is actually expanding. At first glance, it seems straightforward. Things move apart, distances increase, space gets bigger, but the more carefully you look at what cosmologists mean by an expanding universe, the stranger and less intuitive it becomes. Expansion is not an explosion. It is not matter rushing outward into pre-existing emptiness. It is something quieter, more pervasive, and harder to visualize without misleading yourself. When astronomers say the universe is expanding, they mean that the distances between large-scale structures increase over time, even when those structures are not moving through space in the usual sense. Galaxies are not flying away from a central point. There is no center of expansion. Instead, space itself is changing. That distinction matters, because many of our everyday intuitions break down when space becomes an active participant rather than a passive backdrop. A useful starting point is to imagine a grid drawn on a stretchable surface. The dots on the grid represent galaxies. If the surface stretches, the dots move farther apart, even though none of them are sliding across the surface itself. Their positions relative to the surface remain fixed. It is the surface that changes. This analogy is imperfect, but it captures something essential. In cosmic expansion, galaxies are mostly carried along by the stretching of space. On small scales, gravity overpowers this effect. Stars remain bound to galaxies. Galaxies remain bound in clusters. Expansion becomes noticeable only when you look at sufficiently large distances. This is why the expansion of the universe does not tear apart solar systems or even galaxies. The forces holding those systems together are far stronger than the effect of expansion at those scales. For a long time, this expansion was thought to be slowing. The early universe expanded rapidly, then gravity began to pull back, gradually reducing the rate. This picture felt comfortable. Expansion as a leftover momentum from the beginning, gradually losing energy. But the observations forced a change. Expansion is not just continuing, it is accelerating. To understand why that is so puzzling, it helps to examine how expansion is described mathematically. In modern cosmology, expansion is encoded in a single function that describes how the scale of the universe changes with time. This scale factor does not describe size in the everyday sense. It describes how distances between unbound objects grow. If the scale factor grows faster and faster, expansion accelerates. If it grows more slowly, expansion decelerates. Gravity, arising from matter and radiation, always acts to slow the growth of the scale factor. That is built into the equations. To make the scale factor accelerate, something must contribute a repulsive effect. Dark energy does exactly that. What makes this so counterintuitive is that nothing appears to be pushing outward in the way we normally imagine forces acting. There is no preferred direction, no edge, no expanding shell. The acceleration happens everywhere, uniformly. From any galaxy, all sufficiently distant galaxies appear to be moving away, and the farther they are, the faster they recede. This is not because one galaxy is special, it is because expansion acts the same way everywhere. This uniformity is one of the strongest clues that dark energy is tied to space itself rather than to matter within space. As the universe expands, the amount of matter per unit volume decreases. Matter thins out, radiation redshifts and loses energy. But dark energy, at least in the simplest models, does not dilute. Its density remains constant even as space grows. This leads to a peculiar result. As time passes, dark energy becomes more important, not less. Early in the universe, matter dominated. Gravity shaped structure. Galaxies formed. Clusters assembled. Dark energy was present, but it was overwhelmed. Its contribution to the overall dynamics was small. As expansion continued, matter spread out. Gravity weakened over large distances. Dark energy, remaining constant per unit volume, eventually caught up. Then it overtook matter as the dominant influence on expansion. This transition did not happen suddenly. It unfolded over billions of years. There was a long era when gravity and dark energy were roughly balanced on cosmic scales. Expansion slowed, but not as much as gravity alone would predict. Eventually the balance tipped. Dark energy gained the upper hand. Expansion stopped slowing and began to accelerate. This turning point is not marked by any obvious event in the sky. There was no flash, no boundary, no moment you could point to and say, "Here it happened." It is identified only through careful reconstruction of expansion history using distant observations. This subtlety is part of what makes the mystery so persistent. Another source of confusion comes from language. When we hear that the universe is expanding faster, it is tempting to imagine galaxies moving faster through space. But that is not quite right. The velocities involved are not ordinary speeds. They are recession rates tied to distance. Beyond a certain distance, galaxies recede faster than light, not because they are violating relativity, but because space between us and them is expanding. Light emitted by those galaxies still travels locally at the speed of light. It just cannot overcome the stretching of space beyond a certain point. This introduces the idea of a cosmic horizon. There are regions of the universe whose light will never reach us, not because it is blocked, but because the space it must cross expands too quickly. As acceleration continues, this horizon shrinks in a relative sense. More galaxies slip beyond it. The observable universe becomes a smaller fraction of the whole. This is not something that happens suddenly or dramatically. It happens over timescales far longer than human history. But its implications are profound. The future universe becomes increasingly isolated. Each galaxy cluster becomes more alone, surrounded by growing emptiness. This outcome follows directly from how expansion behaves under the influence of dark energy. Yet even as we describe these consequences, we still lack a satisfying explanation for the underlying cause. Why should space expand at all? Why should its expansion accelerate? Why should empty space have energy? These questions reveal a deeper layer of the mystery. In classical physics, empty space is truly empty. It has no properties, it does nothing. In modern physics, empty space is anything but empty. It seethes with quantum fluctuations. Fields exist everywhere. Even the lowest energy state is not zero. Quantum field theory predicts that empty space should have energy. This vacuum energy would act like dark energy, produce an accelerated expansion. But when physicists attempt to calculate the value of this energy, they get an answer that is catastrophically wrong. The predicted value is larger than what is observed by an enormous factor, far beyond any acceptable error. This discrepancy is not a minor technical issue. It is one of the largest mismatches between theory and observation ever encountered in science. It suggests that either our understanding of quantum fields is incomplete, or our understanding of gravity is incomplete, or both. Some researchers suspect that dark energy is not vacuum energy at all, but something more dynamic, a field that changes slowly over time, a property of gravity that behaves differently on large scales, a sign that general relativity needs modification. So far, none of these alternatives have produced clear, testable predictions that outperform the simplest model. The simplest model remains stubbornly effective, a constant dark energy density, uniform, unchanging, quiet. This simplicity is unsettling in its own way. Nature often favours elegance, but it also often reveals deeper structure beneath apparent simplicity. Dark energy may be simple because we are seeing only its surface. Another layer of the mystery lies in timing. Dark energy dominates the universe now, not earlier, not later. This coincidence raises questions. Why should we live at the moment when dark energy and matter densities are comparable? Why not long before or long after? This so-called coincidence problem has no agreed-upon answer. Some suggest selection effects. Some suggest deeper principles not yet understood. Others see it as a sign that our models are incomplete. What makes all of this especially challenging is that expansion itself is not something we can manipulate or experiment on directly. We cannot speed it up or slow it down in a controlled setting. We can only observe it, infer it, and model it. Observational cosmology is a patient science. It relies on light that has travelled for billions of years. It relies on patterns etched into radiation from the early universe. It relies on statistics drawn from vast surveys. This patience matches the subject well. Expansion is slow on human timescales. Acceleration is subtle. The universe reveals its behaviour gradually. As listeners, easing through these ideas, it is worth noticing how different this kind of mystery feels from more familiar ones. There is no villain, no sudden danger, no dramatic confrontation. The mystery of expansion is gentle and persistent. It asks questions without urgency. Why does space behave the way it does? Why does nothingness have structure? Why does the universe grow more quickly as it grows older? These questions do not demand immediate answers. They invite reflection. What we can say with confidence is that expansion is not an illusion. It is not a trick of perspective. It is a measurable, consistent feature of the universe. Dark energy did not create expansion. Expansion was already there. Dark energy changed its character. That distinction matters. because it tells us that the universe's behaviour is not fixed. Different influences dominate at different times. The rules remain the same, but their outcomes evolve. Early on, radiation mattered most, then matter. Now, dark energy. This layered history suggests that the universe is not driven by a single principle alone. It is shaped by the interplay of multiple components, each taking its turn. On the largest scales imaginable, the universe is shaped by a competition so quiet that it leaves no sound, no flash, and no single moment of resolution. It is a long, patient balancing act between two influences that behave in very different ways. One of them is familiar, deeply woven into our everyday experience. The other remains elusive, inferred rather than seen. Together, they determine how the universe grows, stretches, and slowly rearranges itself over time. Gravity and dark energy do not meet head-on like opposing armies. There is no collision, no boundary where one clearly stops and the other begins. Instead, they operate simultaneously, each asserting itself under different conditions, each becoming dominant on different scales. Their interaction is less like a battle and more like a gradual shift in weight, a cosmic tug-of-war where the rope itself is space. Gravity is the older influence in this story, both historically and cosmically. It was gravity that sculpted the early universe into something structured rather than uniform. After the initial expansion cooled enough for matter to exist, gravity began its slow work. Tiny fluctuations in density grew. Regions with slightly more matter pulled in their surroundings. Over time, clouds collapsed, stars ignited, galaxies assembled, and clusters formed. Every familiar structure in the universe owes its existence to gravity's tendency to gather. Dark energy, by contrast, does not gather. It does not form clumps or concentrations. It does not build anything. If gravity is constructive, dark energy is expansive. It does not bind, it separates. But it does so without preference or direction. It does not push objects away from one another directly. It encourages space itself to grow. This difference in behaviour is what allows both influences to coexist, without one immediately cancelling the other out. On small scales, gravity wins decisively. Within galaxies, the gravitational pull between stars overwhelms any effect dark energy might have. The same is true within clusters of galaxies. Even across millions of light years, gravity can dominate, holding structures together against the general expansion of the universe. Dark energy does not disrupt these systems. It does not tear stars from galaxies or galaxies from clusters. Its influence is simply too weak at those scales. But gravity weakens with distance. As you move to larger and larger scales, the density of matter drops. Gravity's grip becomes more diffuse. At some point, the cumulative effect of dark energy, acting uniformly across vast regions of space, becomes comparable to gravity's pull. Beyond that point, dark energy takes over. This transition is not sharp. There is no clear line where gravity ends and dark energy begins. Instead, there is a gradual shift in dominance, dependent on scale and time. Early in the universe's history, gravity ruled almost unchallenged. Matter was dense. Distances were small. Dark energy, even if present, had little opportunity to assert itself. Expansion slowed as gravity pulled back against it. Structure formation was efficient. Galaxies collided and merged. Clusters grew. As the universe expanded, matter spread out. Gravity still worked locally, but its influence over vast distances diminished. Dark energy, remaining uniform, did not weaken in the same way. Eventually the balance tipped. At that point, gravity no longer had the strength to slow expansion on the larger scales. Dark energy began to drive acceleration. The universe entered a new phase, one where separation gradually outweighed attraction. This shift does not mean gravity stopped working. It means that its role changed. Gravity continues to shape local structure. It governs orbits, binds galaxies, and determines the dynamics of clusters. Dark energy does not interfere with these processes. The two influences operate in parallel, each dominating where it is strongest. This coexistence can be difficult to visualize because we are accustomed to thinking of forces as mutually exclusive. In everyday life, one force often overwhelms another completely. But the universe is large enough to allow multiple influences to matter simultaneously in different regimes. To understand this more clearly, it helps to think in terms of density rather than distance alone. Gravity depends on the presence of mass and energy. Where matter is concentrated, gravity is strong. Where matter is sparse, gravity is weak. Dark energy, if it is truly uniform, does not depend on concentration. It exists wherever space exists. As the universe expands, the average density of matter decreases. The density of dark energy remains roughly constant. Over time, this means that dark energy inevitably becomes more important. This is not a sudden takeover. It is a slow drift in relative influence, unfolding over billions of years. One way to describe this mathematically is through how each component contributes to the overall dynamics of the universe. Matter contributes positive energy density and negligible pressure. Radiation contributes energy density and positive pressure. Dark energy contributes energy density and negative pressure. In the equations governing expansion, negative pressure produces a repulsive effect. Not a force in the everyday sense, but a contribution to how space-time curves and evolves. This is why dark energy can oppose gravity without pushing against objects directly. It alters the geometry of space-time in a way that favours expansion. Gravity in this framework is not exactly being defeated, it is being outpaced. On small scales, gravity curves space-time strongly around mass concentrations. This curvature dominates motion locally. On large scales, the uniform contribution of dark energy to space-time curvature becomes more significant. The overall geometry favours accelerated expansion. The result is a universe that is internally structured but externally drifting apart. This dual behaviour has important consequences for the future of cosmic structure. As expansion accelerates, the growth of new structures slows. Gravity becomes less effective at pulling distant matter together. Clusters stop growing. Galaxies outside of bound systems drift away and eventually become unreachable. Over extremely long timescales, existing structures remain intact, but no new large-scale structures form. The universe becomes more fragmented, not through destruction, but through isolation. This outcome is not dramatic in a cinematic sense. There are no explosions, no sudden changes. It is a quiet separation, measured in billions of years. The tug-of-war between gravity and dark energy is not resolved quickly. It continues indefinitely, with gravity reigning locally and dark energy reigning globally. One of the more subtle aspects of this interaction is that gravity itself contributes to the conditions under which dark energy becomes dominant. By forming structures, gravity concentrates matter, leaving larger regions of space relatively empty. Those empty regions are where dark energy's influence is most apparent. In this way, gravity indirectly creates the conditions that allow dark energy to shape the large-scale universe. This is not a contradiction. It is a consequence of how different influences scale with distance and density. Another important aspect of this balance is that gravity is always attractive in general relativity when dealing with ordinary matter and radiation. Dark energy's repulsive effect arises not because it pushes, but because of how its pressure contributes to space-time curvature. This distinction matters when considering alternatives to dark energy. Some theories attempt to explain acceleration by modifying gravity itself. In these models, gravity behaves differently on very large scales. Instead of weakening in a predictable way, it changes character, producing effects that mimic dark energy. So far, such models have struggled to match observations as cleanly as the dark energy framework. They often introduce complications elsewhere, such as inconsistencies with gravitational behavior on smaller scales. The simplicity of dark energy as an additional component remains appealing, even if its origin is mysterious. Still, the tug-of-war metaphor can be misleading if taken too literally. Gravity and dark energy are not forces pulling on a rope. They're contributions to the evolution of space-time itself. Their interaction is encoded in the equations that describe how the universe expands and how matter moves within it. This interaction is smooth, continuous, and largely invisible on human timescales. From our perspective, sitting inside a galaxy bound by gravity, the universe feels stable, orbits persist, structures endure. Dark energy does not intrude on daily experience, but zoom out far enough, and a different picture emerges. One where gravity's reach fades and dark energy quietly stretches the distances between everything that is not already tightly bound. This layered reality can feel unsettling, but it also offers a kind of calm clarity. The universe is not governed by a single principle applied uniformly at all scales. It is governed by a balance, one that shifts with context. This balance is not arbitrary. It arises from the properties of the components involved. Matter behaves one way, dark energy behaves another, space responds accordingly. As scientists continue to refine measurements, they look for signs that this balance might change. If dark energy's properties evolve over time, the future tug-of-war could unfold differently. Acceleration could increase, decrease, or behave in unexpected ways. So far, there is no strong evidence for such change. Dark energy appears steady. That steadiness reinforces the sense that the current cosmic phase will persist. Expansion will continue to accelerate. Gravity will continue to hold local structures together. The two influences will remain locked in their silent coexistence. Understanding this interplay helps clarify why dark energy can be both dominant and subtle. It dominates the fate of the universe without disrupting the structures we inhabit. It shapes the largest outcomes while leaving the smallest details untouched. Long before dark energy entered the scientific conversation, long before astronomers measured distant supernovae or spoke of accelerated expansion, there was already a clue hiding in plain sight. It wasn't discovered through observation, but through mathematics. It wasn't motivated by mystery, but by discomfort. And for decades, it was treated as an embarrassment rather than a hint. The clue came from Albert Einstein. When Einstein developed his general theory of relativity in the early 20th century, he radically changed how gravity was understood. Gravity was no longer a force pulling objects through space. Instead, it was a manifestation of curved space-time. Matter and energy told space how to curve, and curved space told matter how to move. This framework was powerful enough to explain planetary orbits, light bending near massive objects, and the structure of the universe itself. But when Einstein first applied his equations to the universe as a whole, he encountered a problem. The equations did not allow for a static universe. According to general relativity, a universe filled with matter could not simply sit still. Gravity would cause it to collapse inward, or if it were expanding, that expansion would change over time. There was no natural way to keep the universe fixed in size. At the time, the prevailing belief was that the universe was static and eternal. Galaxies had not yet been discovered as separate systems beyond the Milky Way. There was no observational evidence for expansion. The universe, as far as anyone knew, had always existed in roughly the same form. Einstein trusted his equations, but he also trusted the consensus view of the cosmos. Faced with this mismatch, he chose to modify the equations rather than abandon the idea of a static universe. He introduced an additional term, now known as the cosmological constant. This term acted as a kind of repulsive effect, counterbalancing gravity on the larger scales. With the right value, it could hold the universe in a stable, unchanging state. Gravity pulled inward. The cosmological constant pushed outward. The two forces balanced perfectly. At least that was the idea. From a mathematical perspective, the cosmological constant was allowed. There was nothing illegal about it. The equations remained consistent. But its purpose was purely practical. It was added not because it emerged naturally from theory or observation, but because it solved a specific problem Einstein wanted to avoid. This made Einstein uneasy. He later described the addition as artificial, something he introduced reluctantly. Then, in the late 1920s, observations changed everything. Astronomers discovered that galaxies were not fixed in place. They were moving away from one another. The universe was expanding. The static universe Einstein had tried to preserve did not exist. With this realization, the cosmological constant seemed unnecessary. Expansion itself explained why the universe had not collapsed under gravity. Einstein reportedly regretted introducing the term at all, later calling it his biggest blunder. For decades, the story ended there. The cosmological constant was treated as a historical curiosity, a reminder that even great minds can make mistakes. Cosmology moved forward without it. Expansion was accepted. Gravity slowed that expansion. The universe evolved dynamically. The equations worked fine without the extra term. Or so it seemed. What makes this story so compelling in hindsight is not the mistake itself, but how completely it was misinterpreted. The cosmological constant was not wrong because it contradicted observation. It was wrong because it solved the wrong problem at the wrong time. The idea behind it, that empty space might have properties influencing cosmic expansion, was quietly waiting. When dark energy was discovered near the end of the 20th century, cosmologists returned to Einstein's equations with fresh eyes. They noticed something striking. The simplest way to explain accelerated expansion was to reintroduce the cosmological constant, not as a stabilizing force but as a driver of expansion. The same mathematical term Einstein had added to hold the universe still could also make it expand faster. This reinterpretation transformed the narrative. What had once been dismissed as a blunder now looked like a remarkably prescient insight. Einstein had stumbled onto a feature of space-time that would only reveal its relevance decades later, when the universe had expanded enough for its effects to dominate. Whether Einstein would have accepted this reinterpretation is unclear. He died long before dark energy was discovered, but the equations he left behind proved flexible enough to accommodate the new reality. The cosmological constant in modern cosmology represents a constant energy density associated with empty space. It does not change as the universe expands. As space grows, the total amount of this energy increases, leading to accelerated expansion. This behavior matches observations with surprising accuracy. But while the mathematical fit is elegant, the physical interpretation remains deeply troubling. In quantum physics, empty space is not truly empty. Fields exist everywhere, and even in their lowest energy state they exhibit fluctuations. These fluctuations contribute energy. When physicists attempt to calculate the energy of the vacuum using quantum field theory, they find a value that should act like a cosmological constant. The problem is that the calculated value is enormously larger than what is observed. The mismatch is so extreme that it defies intuition. It is not off by a factor of 2 or 10, but by a factor so large that it is often described as the worst theoretical prediction in the history of physics. This discrepancy suggests that something is deeply incomplete in our understanding. Either vacuum energy does not gravitate in the way we expect, or there are cancellations we do not understand, or dark energy is not vacuum energy at all, despite behaving like it observationally. The cosmological constant in this light becomes both a solution and a mystery. It explains the data while highlighting a fundamental gap in theory. This duality mirrors Einstein's original discomfort. He accepted the term mathematically but doubted its physical justification. A century later, physicists find themselves in a similar position. The cosmological constant works, but no one is entirely comfortable with it. Some researchers interpret this as a sign that dark energy is truly constant, a fundamental property of space-time that does not require further explanation. Others see it as a placeholder, a simplified description of something more complex. There are proposals involving dynamic fields that change slowly over time. These fields would behave like dark energy now, but differently in the past or future. There are proposals involving modifications to gravity on large scales. There are proposals involving deeper principles that limit the value of vacuum energy through mechanisms not yet discovered. So far, none of these alternatives have clearly outperformed the cosmological constant model. This persistence is striking. Nature appears to favour the simplest description, even if that description is conceptually unsettling. Another layer of the story lies in timing. The cosmological constant, if it exists, would have been present throughout cosmic history, but its influence would have been negligible early on, when matter and radiation dominated. Only after billions of years would it become important. This delayed relevance explains why it went unnoticed for so long. It also raises questions about coincidence. Why does its influence become dominant now, during the era when observers exist to notice it? Some physicists see this as a selection effect. If dark energy were much stronger, the universe might expand too quickly for galaxies to form. If it were much weaker, it might never dominate at all. The observed value may simply be one that allows complexity. Others find this explanation unsatisfying and seek a deeper reason. The reinterpretation of Einstein's cosmological constant also reshaped how scientists think about mistakes in science. What was once labelled a blunder now looks more like a misapplied insight. The idea was not wrong. The context was. Einstein introduced the term to solve a problem that did not exist. The universe was not static. But the term itself described something real, something that would only become apparent later. This pattern is not unique. Scientific ideas often appear before their relevance is understood. Mathematics sometimes outruns observation. Concepts are introduced for one reason and later find their true home elsewhere. In this sense, the cosmological constant is not an embarrassment. It is a reminder that theory and observation move at different paces. As listeners, resting with this story, it may help to notice how human the process feels. A brilliant mind grapples with equations, adjusts them to fit belief, regrets the adjustment, and leaves behind a tool that future generations reinterpret. There is no villain here, no failure, just an evolving understanding. The question of whether the cosmological constant represents dark energy in its entirety remains open. Observationally it fits, conceptually it troubles. If dark energy is truly constant, the future of the universe is relatively clear. Expansion will continue to accelerate at a steady rate. Structures will drift apart. The universe will become increasingly empty. If dark energy evolves, the future could be very different. Acceleration could slow, stop, or intensify. The universe's fate would change accordingly. Distinguishing between these possibilities requires precision measurements and patience. It requires observing subtle deviations over vast timescales. So far, the universe has offered no clear deviations. Dark energy behaves as if Einstein's discarded term belongs there after all. Whether this reflects a deep truth or a temporary approximation remains to be seen. What is clear is that Einstein's equations, with or without the cosmological constant, continue to frame our understanding of cosmic expansion. The tools developed to explain gravity a century ago remain central to the most current mysteries. The story does not end with vindication or condemnation. It remains open, much like the universe itself. At first glance, empty space seems like the simplest thing imaginable. Nothing is there. No matter, no light, no sound. It feels like the absence of everything rather than something in its own right. For most of human history, that intuition went unchallenged. Space was a backdrop, a stage on which events unfolded, but not an actor in the play. It existed so that things could exist within it, and that was all. Modern physics quietly dismantled that picture. The deeper scientists looked, the more they realized that emptiness is not truly empty. What we call vacuum is not a perfect void. It is a state, and like all physical states, it has properties. Those properties are subtle, hard to measure directly, and deeply counterintuitive, but they refuse to be ignored. This is where the idea of vacuum energy enters the story, not as a dramatic twist, but as an unsettling implication of theories that otherwise work extremely well. In quantum physics, every fundamental field permeates all of space. Even when there are no particles present, the fields themselves do not disappear. They remain, fluctuating gently, unable to settle into complete stillness. This restlessness is not a flaw in the theory. It is a consequence of the uncertainty principle, which forbids a system from having both perfectly defined energy and perfectly defined behavior at the same time. As a result, empty space is alive with microscopic activity. These fluctuations are not directly observable in the way particles are, but their effects can be measured. One of the most famous examples is the Casimir effect, where two closely spaced metal plates experience a tiny force drawing them together, caused by changes in vacuum fluctuations between them. This is not theoretical speculation. It has been measured in laboratories. So the idea that vacuum has energy is not controversial. It is expected. What becomes controversial is what happens when gravity enters the picture. According to general relativity, energy influences space-time. It tells space how to curve and how to evolve. This applies not only to energy carried by particles or radiation, but to any form of energy, including vacuum energy. If empty space contains energy, then empty space should gravitate. This is where things become deeply uncomfortable. Physicists can calculate the expected vacuum energy using quantum field theory. They sum up the contributions of all known fields, accounting for their fluctuations even in empty space. When they do this, they arrive at a number. That number represents the energy density of the vacuum. The problem is not that the number exists, the problem is its size. The predicted value is enormous, not just large but absurdly large. Large enough that if it were real in the way calculations suggest, the universe would be expanding at a rate so extreme that galaxies, stars, and even atoms could never have formed. Clearly that is not what we observe. The vacuum energy that appears to drive cosmic acceleration is incredibly small by comparison. It is tiny, delicately balanced, almost negligible on everyday scales. The difference between the predicted value and the observed value is not a matter of experimental error. It spans many orders of magnitude. The mismatch is so severe that it is often described as the largest discrepancy between theory and observation in all of physics. This is sometimes called the vacuum catastrophe, though the name is misleading. The catastrophe is not that the universe is unstable. It is that our understanding is incomplete. This tension lies at the heart of the dark energy mystery. If dark energy is vacuum energy, then why is it so small? Why does it have the precise value it does? Why does it not overwhelm gravity entirely? Physicists have proposed many ideas to resolve this, but none have achieved consensus. Some suggest that the calculated vacuum energy is real, but that it does not gravitate in the way we expect. Perhaps gravity somehow ignores most of it. Perhaps only differences in vacuum energy matter, not the absolute value. Others propose that different contributions cancel each other out almost perfectly, leaving behind a small residual energy that we observe as dark energy. This cancellation would have to be extraordinarily precise, far beyond what feels natural. There are also ideas involving symmetry principles that force the vacuum energy to be zero or nearly zero under certain conditions. When those conditions break down, a small energy remains. Still others suggest that vacuum energy is not constant but dynamic, evolving slowly over time in ways that are not captured by simple calculations. Each of these ideas attempts to explain the same thing. Why does empty space weigh something, but not too much? To say that vacuum energy has weight is not a metaphor. In general relativity, energy density contributes to gravity. If vacuum energy exists, it affects how space-time curves and expands. This means that even regions with no matter still influence the universe's evolution. This idea challenges everyday intuition in a quiet but persistent way. We're used to thinking of weight as something tied to substance. Something must be there to weigh something. Vacuum energy suggests that nothingness itself contributes, but it is not nothingness. It is a state defined by the lowest possible energy configuration of fields that cannot fully settle. From this perspective, the vacuum is not a void. It is a baseline. The weight of empty space does not press down on objects. It does not pull on planets. It does not distort orbits locally. Its influence is spread uniformly. Only when you consider vast volumes of space does its cumulative effect become apparent. This is why dark energy does not show up in laboratory experiments. The energy density is too small. The gravitational effect is too weak. You would need a volume of space far larger than anything we can isolate on Earth for it to matter. But the universe itself provides that volume. As space expands, more vacuum comes into existence. If vacuum energy density remains constant, then the total amount of vacuum energy increases as the universe grows. This leads naturally to accelerated expansion. This behavior fits the observations with remarkable precision. And yet, it remains deeply unsettling. The discomfort comes not from the idea that empty space has energy, but from how poorly our theories agree on its value. Quantum field theory and general relativity are both extraordinarily successful in their respective domains. Yet when they are combined to predict vacuum energy, they fail spectacularly. This failure is not subtle, it is glaring. Some physicists see this as evidence that our theories are incomplete and that a deeper framework is needed, one that unifies gravity and quantum physics in a way that resolves the vacuum energy problem naturally. Others suspect that the vacuum energy calculation itself is being misinterpreted, that the way energy is defined in quantum field theory does not translate cleanly into gravitational effects. In either case, dark energy becomes a signpost pointing toward new physics. Another unsettling feature of vacuum energy is its apparent constancy. Observations suggest that dark energy density does not change over time, it does not dilute, it does not cluster. It remains uniform as the universe expands. This constancy is difficult to reconcile with many intuitive models. Most forms of energy evolve, matter clumps, radiation redshifts, fields oscillate, vacuum energy just sits there, unchanging. This behavior is exactly what Einstein's cosmological constant describes. The simplicity of this description is both its strength and its weakness. It fits the data cleanly, but it offers no explanation. Why should the vacuum have this particular energy? Why should it be constant? Why should it dominate the universe now? These questions are often grouped under what is called the fine-tuning problem. The value of vacuum energy appears to be finely tuned to allow a universe like ours to exist. Too large, and structure never forms. Too small, and it never dominates. Some physicists find this deeply unsatisfying. They look for mechanisms that naturally set the value without delicate adjustment. Others suggest that we may be seeing only one realization among many. In some theoretical frameworks, different regions of a larger multiverse could have different vacuum energies. We exist in a region where the value happens to allow complexity. This idea is controversial and difficult to test, but it highlights how far the implications of vacuum energy extend beyond traditional cosmology. Regardless of interpretation, the idea that empty space has weight changes how we think about nothingness. It suggests that absence is not neutral, that the baseline state of reality carries influence, that the universe's large-scale behavior is shaped not just by what exists, but by what exists everywhere, even when nothing seems to be. This reframing can feel unsettling, but it also brings a kind of coherence. Dark energy does not need to be an exotic substance drifting through space. It can be space itself, expressing a property that only becomes visible when space becomes vast. That does not solve the mystery, but it narrows it. Instead of asking what dark energy is made of, we ask what empty space is allowed to be. As observations improve, scientists continue to test whether dark energy truly behaves like vacuum energy. They look for signs of change over time. They look for deviations from perfect uniformity. They look for subtle effects that might reveal a deeper structure. So far, the universe has offered no clear surprises in this regard. Dark energy behaves stubbornly, like a cosmological constant. This stubbornness forces us to confront the possibility that the simplest explanation may be the correct one, even if it feels incomplete. Vacuum energy may be real. Empty space may have weight, and the universe's acceleration may be the natural result of that fact. If so, then dark energy is not a new force acting on matter. It is a property of space-time itself. That realization reshapes the conversation. It shifts the mystery from an unknown substance to the nature of nothingness. For a universe that was once thought to be slowing down, the idea of acceleration still feels quietly unsettling. Expansion alone is already a strange enough concept. Space stretching everywhere at once, distances growing without objects needing to move through anything. But acceleration adds another layer of unease. It suggests that expansion is not simply continuing, but intensifying, that something about the universe causes it to pull away from itself more strongly as time goes on. This is not how most physical systems behave. In everyday experience, motion tends to slow unless energy is continuously supplied. Cars coast to a stop, waves fade, even explosions disperse and cool. Acceleration without an obvious source feels wrong in a way that is hard to articulate, and for a long time, cosmologists shared that discomfort. To understand why the universe accelerates, it helps to step back from imagery and focus instead on how expansion is described. Expansion is not about things flying outward into space. It is about the scale of space itself changing with time. When cosmologists say the universe is accelerating, they mean that the rate at which distances increase is itself increasing. If you imagine two distant galaxies not bound by gravity, the space between them grows. 1 billion years later, that space grows faster than it did before. Another 1 billion years later, faster still. The galaxies are not doing anything new, space is. This behavior can be described precisely with equations, but the underlying cause remains conceptually difficult. The key lies in how different components of the universe influence space-time. Matter, radiation, and dark energy all contribute to the universe's energy budget, but they do so in very different ways. Matter has mass and negligible pressure. Radiation has energy and positive pressure. Dark energy, as best we can tell, has energy and negative pressure. Pressure may sound like an odd concept to invoke on cosmic scales, but in general relativity, pressure matters. It contributes to how space-time curves and evolves. Positive pressure, like that from radiation, adds to gravitational attraction. Negative pressure does the opposite. Dark energy's negative pressure is what allows it to drive acceleration. This does not mean dark energy is pushing outward like compressed gas. It means that when its properties are placed into the equations governing expansion, the result favours increasing separation. In simple terms, dark energy resists being diluted. As space expands, matter spreads out and becomes less influential. Radiation loses energy as its wavelength stretches. Dark energy does not thin in the same way. Its energy density remains nearly constant. This constancy has a profound consequence. As the universe expands and becomes emptier, dark energy becomes more important, not less. There is more space, and each unit of space carries the same amount of dark energy. The larger the universe becomes, the more total dark energy it contains. This feedback is what drives acceleration. Early in cosmic history, this effect was negligible. Matter and radiation dominated, expansion slowed, structure formed. Dark energy was present, but it was overwhelmed. Over time, as expansion continued, matter thinned out. Gravity's ability to slow expansion weakened. At a certain point, dark energy caught up. Once dark energy became comparable to matter in its influence on expansion, the universe entered a transitional phase. Expansion slowed less than expected. Eventually the slowdown halted. Then acceleration began. This transition did not require dark energy to change its behavior. It required only that the universe grow large enough for dark energy's constancy to matter. This is one of the most counterintuitive aspects of acceleration. Nothing dramatic needed to happen. No new force switched on. No sudden event altered the laws of physics. The same ingredients were present all along. The balance simply shifted. Another way to think about this is to consider how gravity works over large distances. Gravity depends on mass and density. As matter spreads out, its average density decreases. The gravitational pull it exerts across vast regions weakens. Dark energy, if tied to space itself, does not weaken as space expands. Its contribution per unit volume stays the same. This asymmetry guarantees that dark energy will eventually dominate, no matter how small its energy density is, as long as it is not exactly zero. Acceleration, in this sense, is not surprising. It is inevitable under these conditions. What remains surprising is how well this simple picture matches observations. Measurements of distant supernova, galaxy clustering, gravitational lensing, and the cosmic microwave background all agree on a universe that transitioned from deceleration to acceleration several billion years ago. The timing, the rate, and the behavior all line up with a dark energy component that behaves like a constant. This agreement is striking because it leaves little room for alternatives. Many physicists have proposed models where dark energy changes over time, or where gravity behaves differently on large scales. These models often predict deviations from the simple acceleration pattern. So far, no clear deviations have been observed. Acceleration appears smooth, steady, and persistent. This steadiness has important implications. If acceleration continues indefinitely, the future of the universe is one of increasing separation. Galaxies outside our local group will recede faster and faster. Their light will redshift, dim, and eventually disappear beyond the cosmic horizon. This is not a catastrophic ending. It is a quiet one. Stars will continue to shine within bound systems. Planets will continue their orbits. Life, if it exists elsewhere, will go on locally. But the larger universe will fade from view. Acceleration also affects the formation of new structures. As expansion speeds up, gravity becomes less effective at pulling matter together across large distances. The growth of new galaxy clusters slows and eventually stops. The universe's large-scale structure freezes in place. This freezing is another subtle consequence of acceleration. The universe is dynamic in its expansion, but static in its structure. Understanding why acceleration happens requires accepting that the universe does not behave like familiar systems. There is no conservation of expansion energy in the usual sense. The equations governing space-time allow for behaviors that defy everyday analogy. This can feel unsatisfying, but it is a reminder that intuition is shaped by local experience, not cosmic history. Another source of discomfort lies in the absence of a mechanism we can point to. We can describe acceleration mathematically. We can measure it observationally. But we cannot say what is doing the accelerating in a tangible way. This absence leads some to question whether dark energy is the correct explanation at all. Perhaps acceleration arises from something else. Perhaps our understanding of gravity is incomplete. So far, however, every attempt to explain acceleration without dark energy has faced serious challenges. Modified gravity theories must reproduce the successes of general relativity on small scales, while changing behavior on large scales. This is a difficult balance to achieve. Dark energy, by contrast, leaves gravity untouched locally and modifies only the large-scale dynamics. This minimalism is one of its strengths, yet it also deepens the mystery. If dark energy is simply a constant property of space, why should it have the value it does? Why not zero? Why not much larger? Acceleration makes this question unavoidable. A universe without acceleration would still expand. A universe with too much acceleration would tear itself apart before complexity could arise. The observed acceleration sits in a narrow window. Some physicists interpret this as a coincidence. Others see it as evidence of deeper principles we have yet to uncover. Still others argue that our presence as observers biases what we can observe. None of these explanations are fully satisfying. What acceleration ultimately tells us is that expansion is not a passive aftermath of the universe's beginning. It is an active, ongoing process shaped by the contents of space itself. The universe is not coasting, it is evolving in how it evolves. This layered behavior challenges simple narratives. There was no single expansion phase. There were multiple eras, each governed by different influences. Radiation dominated first, matter followed, now dark energy. Acceleration marks the latest chapter in that sequence. At first glance, dark energy appears almost stubbornly simple. No matter where we look, no matter how far back in time we peer, its behavior seems remarkably consistent. The universe expands, that expansion accelerates, and the rate of acceleration fits neatly with a picture in which dark energy stays the same as space grows. This constancy is mathematically elegant and observationally convenient. It allows cosmologists to describe the universe with a small set of parameters that fit an enormous amount of data. And yet, simplicity can be deceptive. One of the deepest open questions in cosmology is whether dark energy is truly constant, or whether it is slowly changing in ways we have not yet detected. This question may sound technical, but its implications are profound. A constant dark energy points toward one kind of cosmic future. A changing dark energy opens the door to very different possibilities. To understand why this matters, it helps to consider what constant means in this context. A constant dark energy density means that every cubic unit of space contains the same amount of dark energy, regardless of when or where you measure it. As space expands, the total amount of dark energy increases because there is more space to fill, but the density remains fixed. This behavior is exactly what Einstein's cosmological constant describes. In this simplest picture, dark energy does not evolve. It does not weaken. It does not strengthen. It does not respond to the expansion of the universe except by contributing to it. The equations remain clean. Predictions remain stable. So far, observations agree with this picture. Measurements of distant supernovae, galaxy distributions, and the cosmic microwave background all indicate that dark energy's pressure-to-energy ratio is very close to the value expected for a constant. Within current uncertainties, it behaves exactly as if it were unchanging. But within current uncertainties is doing a lot of work in that sentence. Observations are improving, but they are not infinitely precise. Small changes over billions of years could still hide within the error bars. A slowly evolving dark energy could mimic a constant closely enough to escape detection so far. This possibility keeps cosmologists cautious. There are good theoretical reasons to suspect that dark energy might not be perfectly constant. Vacuum energy, while a natural candidate, comes with unresolved problems. The enormous discrepancy between predicted and observed vacuum energy suggests that something is missing from our understanding. A dynamic dark energy could offer a way out. One class of ideas treats dark energy as a field that fills space, somewhat like the fields responsible for other fundamental forces. Unlike those fields, however, this one would evolve extremely slowly. Its energy density would change gradually over cosmic time, influencing expansion in a way that depends on its internal dynamics. In these models, dark energy today might look almost constant. even if it was different in the past or will change in the future. Such fields are often described using an equation that relates their pressure and energy density. For a cosmological constant, that relationship has a specific value. For a dynamic field, the value could differ slightly and might evolve over time. Measuring this relationship precisely is one of the central goals of modern observational cosmology. Astronomers look for subtle deviations in how expansion behaves at different epochs. They compare expansion rates inferred from nearby galaxies with those inferred from very distant ones. They analyse how structure growth responds to expansion over time. They search for inconsistencies that would hint at change. So far, the results have been frustratingly consistent with constancy. This frustration is not disappointment in the usual sense. It is the tension between expectation and reality. Many physicists expected dark energy to reveal complexity. Instead, it behaves with almost suspicious simplicity. That simplicity raises a deeper question. If dark energy is changing, why does it change so slowly? And if it is constant, why does it have the particular value it does? The timing problem looms large here. Dark energy becomes dominant only after billions of years of cosmic evolution. If it were stronger, it would have prevented galaxies from forming. If it were weaker, it might never dominate at all. A changing dark energy could, in principle, explain this timing naturally. It might have been negligible early on, then grown more influential, or it might slowly decay in the future, altering the universe's fate. But nature has not yet offered evidence for such behaviour. Another approach suggests that dark energy might appear constant because it is tied to a fundamental property of space-time that does not evolve. In this view, asking why it changes over time is like asking why the speed of light changes. It does not, because it is built into the structure of reality. This explanation is simple, but it leaves the fine-tuning problem unresolved. Why should this fundamental property have such a small value? Some researchers argue that the question itself may be misplaced. Perhaps there is no deeper reason. Perhaps the value is contingent, not derived from first principles. In some theoretical frameworks, many possible values could exist, and we observe the one compatible with our existence. This line of reasoning is controversial. It shifts the focus from prediction to selection. Some find it unsatisfying. Others see it as a realistic reflection of how a complex universe might behave. From an observational standpoint, the question remains open. Current data strongly favour a constant dark energy, but they do not absolutely rule out slow evolution. Future surveys aim to improve precision significantly. By mapping the positions and motions of millions of galaxies, by measuring weak gravitational lensing with unprecedented accuracy, and by refining distance measurements, astronomers hope to tighten the constraints. If dark energy changes, even slightly, these observations may reveal it. If it does not, the case for a true cosmological constant will grow stronger. Either outcome is unsettling in its own way. A changing dark energy implies new physics, new fields, new dynamics. A constant dark energy implies a deep mystery about vacuum energy and fine-tuning that we do not know how to resolve. There is no comfortable option. It is also possible that dark energy appears constant because our description of gravity is incomplete. In this view, what we call dark energy is not a separate component at all, but a symptom of how gravity behaves on the larger scales. If gravity changes subtly over cosmic distances, the expansion history could mimic the effects of a constant dark energy. Testing this idea is challenging. Modified gravity models must reproduce all the successes of general relativity locally while deviating only on the larger scales. So far, no alternative has matched observations as cleanly as the dark energy framework. As measurements become more precise, the distinction between constant dark energy, evolving dark energy, and modified gravity will become clearer. For now, the universe remains frustratingly quiet on the matter. Dark energy does not announce itself with variability. It does not flicker or drift in ways we can easily detect. It sits in the equations, steady and unchanging, shaping expansion with a light but persistent touch. This steadiness makes it tempting to accept constancy as the final answer, but science has learned to be cautious of conclusions drawn too early. History is full of cases where apparent simplicity concealed deeper structure. Atoms were once thought indivisible. Space and time were once thought absolute. The universe itself was once thought static. Dark energy may join that list, or it may remain stubbornly simple, forcing us to accept that some aspects of reality are not derived from deeper mechanisms we can easily uncover. As listeners, there is no need to resolve this tension. It is enough to recognize it. The question of whether dark energy changes over time is not just about cosmic expansion. It is about the nature of explanation itself. Do we expect every parameter to have a cause we can articulate? Or do we accept that some features of the universe simply are? The answer to that may unfold slowly, over decades of observation and thought. Studying something that cannot be seen, touched, isolated, or directly detected requires a very particular kind of patience. Astronomers are used to this, more than most scientists. Long before dark energy entered the picture, much of astronomy already relied on inference rather than direct interaction. Stars cannot be sampled. Galaxies cannot be visited. The universe offers no knobs to turn or switches to flip. Everything must be learned from light, motion, and patterns that unfold slowly over time. Dark energy pushes this approach to its limit. Unlike stars or gas clouds, dark energy emits no light at all. It does not absorb light. It does not bend light locally in a way that can be traced back to a source. It leaves no tracks in detectors. There is no signal you can point to and say with certainty, that is dark energy itself. Instead, astronomers must study it indirectly, by watching how the universe behaves as a whole and asking what must exist to make that behavior possible. This means that studying dark energy is less like finding a hidden object, and more like solving a puzzle where most of the pieces are missing, and the image on the box is incomplete. The primary tool astronomers use is distance. Measuring how far away things are and how those distances change with time is the backbone of dark energy research. This may sound simple, but measuring cosmic distances is one of the most challenging tasks in all of science. There is no single method that works at all scales. Instead, astronomers build what is often called a distance ladder, a sequence of techniques that overlap and reinforce one another. Each rung of the ladder works over a certain range and must be calibrated carefully against the others. For nearby stars, distances can be measured using parallax, the tiny shift in position caused by Earth's orbit around the Sun. This method is geometrically clean and does not rely on assumptions about the stars themselves. It forms the foundation of the ladder. For more distant stars and galaxies, astronomers rely on objects with predictable brightness, such as certain types of variable stars and supernovae. These act as reference points, allowing distances to be inferred from observed brightness. Dark energy enters the story when astronomers use these distance measurements to reconstruct how the universe expanded over time. By comparing distances to galaxies at different redshifts, scientists can trace how expansion has changed across billions of years. Redshift itself is another crucial tool. As space expands, light travelling through it is stretched, increasing its wavelength. This stretching shifts light toward the red end of the spectrum. The amount of redshift tells astronomers how much the universe has expanded since the light was emitted. By combining redshift and distance, astronomers can build a detailed map of expansion history. Dark energy reveals itself when this map does not match what gravity alone would predict. But distance and redshift are only the beginning. Another major approach involves studying the large-scale structure of the universe. Galaxies are not scattered randomly. They form patterns shaped by the competing influences of gravity and expansion. These patterns encode information about how the universe evolved. In the early universe, matter was distributed almost uniformly, with tiny fluctuations in density. Over time, gravity amplified these fluctuations, drawing matter into denser regions. Expansion worked against this process, pulling matter apart. Dark energy changes the balance. By studying how structures grow and how that growth slows over time, astronomers can infer the influence of dark energy. If expansion accelerates, gravity has less time and opportunity to build large structures. The universe's architecture becomes frozen in place earlier than it otherwise would. To study this, astronomers conduct massive galaxy surveys, mapping the positions of millions of galaxies across enormous volumes of space. These surveys reveal subtle statistical patterns, including characteristic clustering scales that act as cosmic yardsticks. One such pattern arises from sound waves that traveled through the hot plasma of the early universe. These waves left an imprint on the distribution of matter, creating a preferred separation scale between galaxies. By measuring this scale at different epochs, astronomers can track how expansion has progressed. Dark energy affects how this scale appears at different redshifts. Gravitational lensing provides another indirect method. When light from distant galaxies passes through regions of space filled with matter, its path is bent. This bending distorts the shapes of background galaxies in subtle ways. By analysing these distortions statistically, astronomers can map the distribution of matter, including dark matter. Dark energy influences this process by altering how structures grow and how distances relate to lensing effects. Measuring lensing across different redshifts helps constrain how expansion has changed. What makes gravitational lensing particularly valuable is that it does not rely on assumptions about the intrinsic brightness of objects. It depends only on gravity and geometry. This independence makes it a powerful cross-check. Another approach involves the cosmic microwave background, the faint radiation left over from the early universe. While this radiation originates from a time long before dark energy became important, it still carries indirect information about dark energy through geometry. The pattern of temperature fluctuations in this background depends on the universe's overall curvature and composition. Dark energy influences how space has expanded since that radiation was emitted, altering how those patterns appear today. By comparing the observed patterns with theoretical predictions, astronomers can infer how much dark energy must exist to make everything consistent. None of these methods, taken alone, can fully characterize dark energy. Each has limitations, each depends on assumptions, each carries uncertainties. What gives scientists confidence is that all of these methods point in the same direction. This convergence is crucial. It means dark energy is not an artifact of a single measurement technique. It is not a quirk of supernova, or a bias in galaxy surveys, or a misinterpretation of background radiation. It is a feature that emerges no matter how the universe is examined. Still, studying the invisible comes with persistent challenges. One of the biggest is separating the effects of dark energy from other influences. Expansion history depends not only on dark energy, but also on matter density, radiation, and the properties of gravity itself. Untangling these contributions requires careful modelling and precise data. Small uncertainties can propagate. A slight error in distance calibration can mimic changes in expansion. Unaccounted for astrophysical effects can bias measurements. Dust, evolution of stellar populations, and selection effects all complicate the picture. Astronomers spend enormous effort identifying, modelling, and correcting for these issues. Another challenge lies in the fact that dark energy operates on the larger scales, where cosmic variance becomes important. We observe only one universe, and only a finite portion of it. Statistical fluctuations on the larger scales cannot be averaged away by observing more objects. This limits precision. Despite these challenges, progress continues steadily. New telescopes, new surveys, and new analysis techniques improve constraints year by year. Space-based observatories reduce atmospheric interference. Larger data sets reduce random errors. better theoretical models refine interpretation. What has not changed is the fundamental indirectness of the task. Astronomers are not looking for dark energy itself. They are looking for its shadow, cast across cosmic history. This approach requires humility. It requires accepting that some questions may not yield clear answers quickly. It requires working with probabilities rather than certainties. In this sense, dark energy research resembles detective work more than experimentation. Clues are scattered across space and time. No single clue solves the case. Only by assembling many pieces does a coherent picture emerge. It also requires collaboration on an enormous scale. Modern dark energy studies involve international teams, shared data, and cross-checked analyses. No single observer or instrument can tackle the problem alone. This collective effort reflects the scale of the mystery itself. Another subtlety is that astronomers must remain open to the possibility that dark energy is not what they think it is. Every measurement is framed within a model. If the model is incomplete, the interpretation may be misleading. For this reason, researchers test multiple models against the same data. They ask whether different assumptions could explain observations equally well. They search for inconsistencies that might hint at new physics. So far, the simplest model continues to survive. This persistence does not bring comfort so much as focus. It narrows the range of possibilities. It tells astronomers where not to look, even as it leaves open the question of where the deeper explanation lies. Studying the invisible also forces astronomers to confront the limits of observation. Some aspects of dark energy may never be directly testable. If it truly is a constant property of space-time, there may be no experiment that reveals its origin. This possibility is difficult to accept, especially in a scientific culture built on explanation. Yet astronomy has long dealt with limits. We cannot see beyond the observable universe. We cannot observe the universe before it became transparent. We cannot rewind cosmic history. Within those limits, understanding still advances. Dark energy research sits at the boundary between what can be measured and what can be explained. It occupies a space where observation is precise, but interpretation remains open. For listeners easing through these ideas, it may help to notice that this is not a failure of science. It is science doing exactly what it is meant to do, measuring carefully, questioning assumptions, following evidence even when it leads somewhere uncomfortable. Astronomers do not claim to see dark energy. They claim to see a universe that behaves as if dark energy exists. That distinction matters. It leaves room for surprise. As instruments improve and data accumulates, the invisible may reveal new hints. Patterns may shift. Subtle deviations may emerge. Or the universe may continue to confirm the simplest picture, forcing us to accept that some truths are deeply simple and deeply strange at the same time. Either way, the effort to study the invisible continues, not because certainty is guaranteed, but because understanding is always provisional. From here, the natural question becomes what all of this implies for the universe's long-term future. If dark energy remains as it appears, what happens next? When people hear that dark energy dominates the universe, the instinctive reaction is often to imagine something dramatic, even catastrophic. A force that outweighs everything else sounds like it should bring sudden endings or violent change, but the reality of what dark energy means for the fate of everything is quieter, slower, and in many ways more unsettling precisely because of how little urgency it contains. Dark energy does not rush the universe toward an ending, it stretches it toward one. To understand what lies ahead, it helps to remember that cosmic fate is not decided by a single moment or event. It is shaped by trends that unfold over unimaginable lengths of time. The universe does not flip a switch from one state to another. It drifts, gradually and persistently, guided by whatever influence dominates at a given era. Right now, that influence is dark energy. If dark energy behaves as current observations suggest, remaining constant over time, then the universe's future is dominated by accelerated expansion that never stops. Space continues to stretch. Distances between unbound objects continue to grow. Galaxies outside of local gravitational groups drift farther away, their light becoming fainter and redder until it can no longer reach us. This future is often described as a universe growing colder, emptier, and more isolated. Not because anything is destroyed, but because everything becomes separated. In the near future, on cosmic timescales, very little changes. Our galaxy remains intact. Nearby galaxies bound by gravity remain visible. Stars continue to form, live, and die. Planets continue their quiet orbits. Dark energy has no effect on these processes. Acceleration matters only on very large scales. But given enough time, even gentle influences accumulate. As expansion continues to accelerate, galaxies outside our local group move beyond the observable horizon. Their light stretches so much that it fades into invisibility. Eventually, an observer within our galaxy would see fewer and fewer external galaxies, until the universe appears mostly empty beyond the Milky Way and its immediate companions. This does not happen suddenly. It unfolds over tens of billions of years. From within such a future galaxy, the universe would look radically different. The cosmic microwave background, already faint, would stretch beyond detectability. Evidence of the Big Bang itself would fade from view. The large-scale structure of the universe would become inaccessible. This leads to an interesting implication. Future observers might have great difficulty reconstructing cosmic history. Without access to distant galaxies or background radiation, the universe could appear static and eternal once again, much as it did to astronomers before expansion was discovered. Dark energy, in this sense, not only shapes the future, but erases evidence of the past. Beyond isolation, there is the question of structure formation. Gravity once pulled matter together efficiently, forming galaxies and clusters. As expansion accelerates, this process slows. Matter has less time to fall inward before being carried away by expanding space. Eventually, large-scale structure formation effectively stops. The universe reaches a point where gravity can no longer assemble new clusters from distant matter. Existing structures remain bound, but no new ones form. The universe becomes dynamically quiet on large scales. Stars will still form for a long time, fueled by existing gas reservoirs. Over trillions of years, however, gas supplies diminish. Star formation slows. Existing stars age, burn out, and leave behind remnants. White dwarfs cool. Neutron stars fade. Black holes persist. This long-term future is shaped not directly by dark energy, but by the conditions dark energy creates. Expansion accelerates. Matter becomes isolated. Energy becomes harder to concentrate. Eventually, the universe approaches what is sometimes called a heat death, a state of maximum entropy where useful energy differences disappear. Everything becomes evenly spread, cold, and inert. Dark energy does not cause heat death directly. It facilitates it by preventing matter from reassembling into new structures. This outcome is often misunderstood as a kind of ending, but it is more accurate to describe it as an asymptote. The universe does not reach a final moment. It approaches a state where nothing significant changes. Time continues, but events become rare. This scenario depends crucially on dark energy remaining constant. If dark energy behaves differently, the fate of the universe could change dramatically. If dark energy were to weaken over time, acceleration could slow or even stop. Expansion might resume a more gentle pace. In some models, gravity could regain influence on large scales, allowing new structure formation or even eventual collapse. If dark energy were to strengthen, acceleration could increase. In extreme cases, expansion could become so rapid that even bound structures would eventually be torn apart. Galaxies, stars, planets, and eventually atoms themselves could be separated. This hypothetical outcome is sometimes called a big rip, though the name suggests violence that unfolds far more slowly than the term implies. Even in such scenarios, destruction would occur over immense timescales. Current observations do not favour such extreme behaviour. They point toward dark energy remaining stable, but the fact that different futures are possible highlights how sensitive cosmic fate is to the properties of dark energy. What makes this particularly striking is that dark energy affects the fate of everything without interacting with most things at all. It does not touch stars or planets directly. It does not interfere with chemistry or biology. It shapes destiny by shaping distance. This is a very different kind of influence from what we usually imagine when thinking about cosmic forces. Gravity builds, dark energy separates. Another implication of dark energy's dominance is that the universe's fate is no longer determined solely by how much matter it contains. Before acceleration was discovered, cosmologists believed that knowing the universe's density would reveal its destiny. Enough matter meant collapse. Too little meant endless expansion. Dark energy breaks that link. A universe can be dense and still expand forever. It can be flat and still accelerate. Geometry no longer dictates fate. Instead, fate depends on the nature of dark energy. This shift has philosophical implications as well. It means that the future of everything is governed by something we do not understand. The universe's ultimate direction depends on a component whose origin, nature and behaviour are still mysterious. This does not make the future chaotic or unpredictable in a practical sense. On human timescales, the universe is extraordinarily stable. It does mean that our deepest cosmic predictions rest on incomplete knowledge. There is also a subtle emotional dimension to this realization. The universe expanding forever into isolation can feel lonely, as if everything meaningful is being slowly pulled apart. But that interpretation comes from projecting human values onto cosmic processes. From another perspective, dark energy simply allows the universe to continue. It avoids collapse. It prevents catastrophic endings. It provides a gentle, extended future rather than a violent one. There is no cosmic rush. The fate shaped by dark energy unfolds so slowly that it is almost static from a human viewpoint. Entire civilizations could rise and fall without noticing any change in cosmic acceleration. Even the lifetime of the sun is short compared to the timescales involved. Dark energy sets the direction, not the tempo. Another important implication concerns horizons. As acceleration continues, there are limits to what can ever be observed or influenced. Regions of space become causally disconnected. Signals sent today will never reach certain distant regions, no matter how long one waits. This introduces a permanent boundary to interaction. In practical terms, this means that the observable universe shrinks in a relative sense, not because space contracts, but because acceleration limits what remains accessible. This has consequences for information, communication, and potential future exploration. Even hypothetical civilizations with advanced technology would face hard limits imposed by cosmic expansion. Dark energy defines the ultimate scale of connection. It is worth emphasizing again how gentle this all is. There is no moment when galaxies suddenly vanish, no instant when the universe changes character. Everything happens gradually, continuously, almost imperceptibly. This gentleness is part of what makes dark energy so difficult to grapple with. It does not fit the narrative structures we tend to use when thinking about endings. There is no final scene. The universe simply keeps going, becoming larger, emptier, quieter. Some physicists find this deeply unsatisfying. They prefer futures with symmetry, cycles, or dramatic resolution. Others find it fitting. A universe that began quietly, expanded, cooled, and continues expanding quietly again. Whether this future feels bleak or peaceful depends largely on perspective. What matters scientifically is that dark energy gives us a framework to think about cosmic fate in concrete terms. It allows predictions to be made, even if those predictions rest on assumptions that may be revised. As observations improve, these predictions may sharpen or change. If dark energy remains constant, the long-term future is relatively clear. If it changes, the future becomes more open-ended. Either way, dark energy ensures that the universe's fate is not governed by gravity alone. This realization reframes how we think about permanence and change. Structures we consider stable are stable only locally and temporarily. On the larger scales, separation is the rule. Yet within that separation, complexity persists for a very long time. Stars burn, planets orbit. Life, where it arises, unfolds its own stories. Dark energy does not interfere with these narratives. It simply sets the background against which they play out. This is an important point to sit with. Dark energy determines the fate of everything in the abstract sense, but it does not determine the meaning of anything. It shapes the canvas, not the content. The next question that naturally arises is whether this future is truly inevitable, or whether there are more extreme possibilities hidden within the uncertainty. If dark energy were to behave differently, could the universe end not in quiet isolation, but in something more dramatic? When people hear that the universe is accelerating, the imagination often jumps to extremes. Expansion speeding up sounds as though it must eventually cross some invisible threshold, turning gentle separation into something violent. If space keeps stretching faster and faster, the question feels unavoidable. Could it go too far? Could the universe, instead of simply growing emptier, eventually pull itself apart? This idea has a dramatic name, often used in popular explanations, but the underlying physics is quieter and more subtle than the phrase suggests. There is no single moment where everything suddenly breaks. There is no cosmic tearing sound. If such a fate were possible, it would unfold gradually, step by step, over enormous spans of time. To understand whether the universe could tear itself apart, it helps to return to what acceleration really means and what it depends on. Expansion alone does not threaten structure. The universe has been expanding since its earliest moments, and yet galaxies, stars and planets formed quite successfully. Acceleration by itself is not automatically destructive either. What matters is how strong that acceleration becomes and how it evolves over time. At present, dark energy appears to be gentle. Its effect is dominant only on the larger scales. Within galaxies, gravity is vastly stronger. Even within clusters of galaxies, gravitational binding easily overwhelms the tendency of space to expand. This balance is not delicate, it is robust. So the question is not whether the universe is tearing itself apart now. It clearly is not. The question is whether dark energy could change in such a way that its influence grows strong enough to overcome gravity even on small scales. This possibility arises only if dark energy is not constant. If dark energy remains exactly as it appears today, behaving like a cosmological constant with steady energy density and fixed negative pressure, then the answer is simple. No, the universe will not tear itself apart. Expansion will accelerate, but the acceleration will remain limited. Bound structures will stay bound indefinitely. In this scenario, galaxies remain intact. Stars continue their lives. Atoms remain atoms. Space stretches between structures, not within them. The more dramatic possibilities emerge only if dark energy evolves over time in a specific and extreme way. Some theoretical models allow for dark energy whose pressure becomes more negative as time goes on. In these models, the repulsive effect grows stronger rather than staying constant. Expansion accelerates faster and faster, not just relative to gravity on large scales, but eventually relative to gravity everywhere. If this were to happen, the sequence of events would be gradual and orderly, even if the outcome sounds alarming. First, the expansion would overwhelm gravity between clusters of galaxies. Those clusters, currently bound, would begin to drift apart. Galaxies that were once neighbours would no longer remain gravitationally associated. Later, if acceleration continued to increase, it could begin to affect individual galaxies. Stars orbiting within galaxies would find their orbits destabilized as the expansion of space begins to compete with gravitational attraction. Still later, if acceleration became extreme, planetary systems could be disrupted. Planets would drift away from their stars. Eventually, even atomic bonds could be overcome, separating electrons from nuclei. This sequence is sometimes described as a cosmic unbinding rather than a tearing. Structures do not explode, they simply fail to hold together. What makes this scenario especially unsettling is not its violence, but its inevitability once certain conditions are met. If dark energy's influence grows without bound, nothing with finite binding energy can resist forever. This hypothetical future is often referred to as a big rip, though the term exaggerates the drama. Nothing rips suddenly. Everything gently loses coherence. It is important to emphasize that this is not the expected outcome based on current evidence. Observations strongly favor dark energy behaving like a constant. There is no indication so far that its pressure is becoming more negative over time. Measurements of expansion, structure growth, and cosmic geometry are all consistent with a stable acceleration. In other words, the conditions required for the universe to tear itself apart are not supported by data. Still, scientists explore these possibilities not because they are likely, but because they help clarify what dark energy could be and what its properties imply. Exploring extreme cases is a way of testing understanding. Another reason these ideas persist is that they highlight how sensitive cosmic fate is to dark energy's behavior. A small change in its properties can lead to vastly different outcomes over long timescales. This sensitivity underscores how incomplete our understanding still is. The idea of the universe tearing itself apart also raises questions about scale and time. Even in the most extreme scenarios, such an outcome would not occur anytime soon. We are talking about tens of billions of years in the future, at minimum, and often far longer. On human timescales, on planetary timescales, even on stellar timescales, the universe would appear unchanged. This distance in time matters, because it reminds us that these questions are not about imminent danger. They're about the ultimate behavior of space-time itself. There is also a conceptual trap worth avoiding. It is tempting to imagine expansion as a force acting on objects, pulling them apart. But expansion does not work that way. Objects are not dragged through space by expansion. Space itself changes. For bound systems, the internal forces defining those systems shape how space behaves locally. Expansion is effectively suppressed within them. Only if the underlying geometry of space-time were to change radically would this suppression fail. This brings the discussion back to gravity and general relativity. In Einstein's theory, gravity is geometry. If dark energy alters geometry strongly enough, the balance could change. So far, there is no sign that it does. Another scenario sometimes discussed involves a sudden change in dark energy's behavior, where its pressure flips sign or its density changes abruptly. Such transitions are theoretically possible in some models, but they lack observational support. Nature, as far as we can tell, prefers smooth behavior. The universe's expansion history so far shows no sudden jumps, no abrupt phase changes in dark energy. Everything appears gradual, continuous, and stable. This stability argues against catastrophic futures. It is also worth noting that even if dark energy were to evolve, it could evolve in the opposite direction. It could weaken, acceleration could slow, expansion could become gentler over time. In some models, dark energy could even decay away, leaving gravity to dominate once more. Such a future would not involve tearing, but perhaps renewed structure formation or eventual collapse, depending on circumstances. Again, current evidence does not favour this either. What observations tell us, with increasing confidence, is that dark energy is remarkably well behaved. It does not fluctuate. It does not show signs of instability. It does not hint at runaway behaviour. The idea of the universe tearing itself apart is therefore best understood as a boundary case, a reminder of what could happen under extreme assumptions, not prediction. Why, then, does this idea persist in discussions of dark energy? Part of the reason is that it captures attention. It dramatizes an otherwise subtle topic. But a deeper reason is that it forces us to confront how little we truly know about the nature of dark energy. As long as dark energy remains unexplained, its future behaviour cannot be known with absolute certainty. Even if current data strongly favour constancy, science remains cautious. The universe has surprised us before. Before acceleration was discovered, no one expected it. Before dark energy entered the picture, gravity alone seemed sufficient. The history of cosmology is a history of comfortable assumptions overturned by careful observation. This does not mean we should expect catastrophe. It means we should remain open. There is also a philosophical dimension to this question. The idea that the universe could tear itself apart challenges the notion of permanence at the deepest level. Not only are structures temporary, but even the bonds between fundamental particles could be contingent. This idea can feel unsettling, but it is not unique to dark energy. Nuclear decay, particle interactions, and even space-time itself are subject to laws that do not guarantee eternal stability. Physics does not promise permanence, it describes behaviour. Another subtle point is that tearing apart implies an external force acting on the universe. But there is nothing external. If such a fate were to occur, it would be the universe responding to its own internal properties. The universe would not be destroyed by something else. It would evolve according to its own rules. This framing removes some of the drama. There is no cosmic enemy. There is only structure responding to geometry. As listeners resting with these ideas, it may help to notice how different this is from most stories about endings. There is no villain, no conflict, no climax. There is only change unfolding over time. Whether the universe ends in quiet isolation, dramatic unbinding, or something else entirely depends on details we are still uncovering. At present, the safest conclusion is also the least sensational. The universe is not on track to tear itself apart. Dark energy, as far as we can measure, is stable. The most likely future is one of continued acceleration, increasing separation, and long-term quiet. That conclusion is not boring. It is profound. It tells us that the universe's story is not one of sudden endings, but of gradual transformation. Still, exploring extreme possibilities helps sharpen understanding. It forces us to ask what assumptions underpin our models. It clarifies which features of dark energy matter most, and it naturally leads to another question. If dark energy is so dominant, so subtle, and so difficult to understand, why do we still know so little about it? Why, after decades of observation, does it remain such a mystery? Even after decades of observation, increasingly precise measurements, and enormous theoretical effort, dark energy remains stubbornly undefined. We can describe what it does with confidence. We can quantify how much of it there appears to be. We can model its influence on the expansion of the universe with remarkable accuracy. And yet, when asked what dark energy actually is, in a physical sense, the honest answer remains simple and uncomfortable. We do not know. This is not ignorance in the casual sense. It is not a matter of missing data or insufficient technology alone. It is a deeper kind of not knowing, rooted in the limits of our current theories and the unusual nature of the problem itself. Dark energy sits at an intersection where our most successful ideas struggle to meet. One reason dark energy resists explanation is that it does not behave like anything else we know. Physics has a long history of uncovering unseen components of reality. When atoms were proposed, they explained chemical behaviour. When neutrinos were suggested, they conserved energy in particle reactions. When dark matter was inferred, it behaved like matter, invisible but gravitationally active. Dark energy fits none of these patterns. It does not clump. It does not dilute. It does not interact with matter or radiation in any detectable way, other than through gravity on the larger scales. It does not form structures or leave localized signatures. It is everywhere, uniform and quiet. This makes it extraordinarily difficult to probe. Most discoveries in physics rely on interaction. You learn what something is by how it collides, scatters, absorbs, or emits. Dark energy does none of these. It does not announce itself in detectors. It does not show up in particle accelerators. It does not leave tracks. All we have are its large-scale consequences. Another major obstacle lies in the mismatch between theory and observation. Quantum field theory, which successfully describes the behavior of particles and fields, predicts that empty space should have energy. That energy should gravitate. In principle, this vacuum energy should act like dark energy. But when physicists calculate its expected value, they get an answer that is wildly wrong. This is not a small discrepancy that might be fixed with better measurements or minor adjustments. It is an enormous gulf. The predicted energy density of the vacuum exceeds the observed value of dark energy by an almost unimaginable factor. This failure is not subtle, it is catastrophic. And yet, both quantum field theory and general relativity work exceptionally well in every other tested regime. They are among the most successful theories ever constructed. Dark energy exposes a place where they clash violently. This suggests that our theoretical framework is incomplete. We are trying to combine two theories that were not designed to work together in this context. General relativity treats energy as a source of space-time curvature. Quantum field theory treats energy in a way that does not account cleanly for gravity. Dark energy lives precisely where those two descriptions must meet. Until a deeper theory unifies gravity and quantum physics in a consistent way, dark energy may remain unexplained. There is also the problem of scale. Dark energy matters only on the largest scales imaginable. Its influence becomes noticeable only when averaging over hundreds of millions of light years. On smaller scales, it is irrelevant. This means that experiments designed to test physics locally are largely useless for probing dark energy's nature. Laboratories are too small. Solar systems are too small. Galaxies are too small. We are trying to understand something whose arena is the universe itself, that severely limits experimental control. We cannot vary conditions. We cannot isolate variables. We cannot repeat the universe with slightly different parameters to see what changes. We get one universe, one expansion history, one set of conditions. This makes inference slow and uncertain. Another difficulty lies in the fact that dark energy is defined largely by what it is not. It is not matter. It is not radiation. It is not dark matter. It does not behave like any known field that interacts with particles in familiar ways. This negative definition is unsatisfying, but it reflects the state of knowledge. Dark energy is the name we give to whatever causes accelerated expansion. If future observations reveal that acceleration arises from modified gravity, then dark energy may disappear as a separate concept. If acceleration is driven by a dynamic field, dark energy will be reclassified. If it truly is vacuum energy, then it will remain, but with a deeper explanation still missing. At present, dark energy is a category, not a substance. There is also the coincidence problem, which complicates attempts at explanation. Dark energy dominates the universe now at this particular epoch, not in the distant past, not overwhelmingly in the far future. Right now its energy density is comparable to that of matter. This timing feels strange. If dark energy is constant and matter density decreases over time, then there is only a narrow window when the two are comparable. We happen to live in that window. Why? Some physicists argue that this coincidence demands explanation. Others argue that it does not. Perhaps observers can only arise during eras when structure exists, which requires matter dominance early on and dark energy dominance late enough not to prevent galaxy formation. This line of reasoning shifts explanation away from fundamental mechanism and towards selection effects. Many find this unsatisfying, but it highlights how dark energy pushes against traditional expectations of explanation. Another reason we still do not know what dark energy is lies in the limits of observation. Although measurements have become incredibly precise, they still probe only certain aspects of dark energy's behaviour. We measure its average effect on expansion. We constrain how it might change over time. We test whether it clusters. So far, all results are consistent with extreme simplicity. This consistency leaves little to work with. If dark energy showed variability, anisotropy, or interaction, those features would offer clues. Instead, it behaves like a constant background. The very feature that makes dark energy easy to model makes it hard to understand. It is also worth noting that many proposed explanations for dark energy are mathematically flexible. Dynamic fields can be tuned to mimic a constant. Modified gravity theories can be adjusted to reproduce the same expansion history. Multiverse ideas can accommodate any value. This flexibility is not a strength. It makes it difficult to distinguish between competing ideas using current data. When many theories can explain the same observations, explanation loses sharpness. Another obstacle is conceptual. Dark energy challenges deeply ingrained intuitions about cause and effect. We are used to forces arising from objects or interactions. Dark energy may arise from the structure of space-time itself. If that is the case, asking what dark energy is may be like asking what time is made of. The question assumes a kind of answer that may not exist. This does not mean the question is meaningless. It means it may require a different framing. In general relativity, gravity is not a force with a substance. It is geometry. Perhaps dark energy is similar, not something added to space-time, but something space-time does. If so, explanation may come not from identifying a new entity, but from understanding space-time more deeply. This idea is appealing, but it remains vague without a concrete theory to support it. The lack of a clear experimental path forward also contributes to the uncertainty. Particle physics progresses through collisions, chemistry through reactions, biology through manipulation of systems. Dark energy offers no comparable handle. Progress depends on incremental improvements in observation, often requiring decades-long projects, massive collaborations, and careful statistical analysis. This pace can feel slow, especially compared to fields where experiments can be designed and executed relatively quickly. Yet this is the nature of cosmology. Another reason dark energy remains mysterious is historical. For most of the 20th century, cosmology focused on matter, radiation, and gravity. The possibility that empty space itself could dominate cosmic dynamics was not taken seriously. When acceleration was discovered, it forced a sudden expansion of the conceptual landscape. Ideas that had been peripheral or speculative moved to center stage. Theoretical frameworks had not been developed with this possibility in mind. Dark energy arrived before we were ready for it. This mismatch between observation and theory is not unique. It has happened before in physics. Quantum mechanics arrived before a philosophical framework existed to make sense of it. Relativity challenged intuitions that took decades to adjust. Dark energy may represent a similar moment. It may take new concepts, not just new data, to understand it. There is also the possibility that dark energy is not a single thing at all. It may be a placeholder for multiple effects that combine to produce accelerated expansion. Perhaps vacuum energy contributes some part. Perhaps gravity behaves slightly differently on large scales. Perhaps additional fields play a role. If so, the simplicity we observe may be deceptive, masking underlying complexity. Disentangling such contributions would be extremely difficult. Despite all this, it is important to recognize what we do know. We know that accelerated expansion is real. We know that it cannot be explained by matter and radiation alone. We know that whatever causes it behaves uniformly and persistently. We know that it influences the fate of the universe. This knowledge is not trivial. The gap lies between description and explanation. Science is comfortable with such gaps, even if they feel unsatisfying. History shows that gaps often persist for long periods before being resolved, sometimes in unexpected ways. Dark energy may require a radical shift in how we think about space, time, and energy. Or it may require a subtle correction to existing theories, or it may force us to accept that some parameters are not derivable from deeper principles. We do not yet know which. What makes dark energy particularly humbling is that it dominates the universe while remaining almost completely inaccessible. The most influential component of reality is also the least interactive. This inversion of expectation is difficult to reconcile with human intuition. It reminds us that the universe is not obligated to align with our preferred modes of understanding. As listeners, it may help to notice that not knowing what dark energy is does not undermine the value of what has been learned. On the contrary, it highlights how far understanding has already progressed. A century ago, expansion itself was unknown. A few decades ago, acceleration was unimagined. Today, dark energy is measured with precision. Each step revealed a deeper mystery. There is no reason to assume the process stops here. Whether dark energy turns out to be vacuum energy, a new field, a feature of space-time, a modification of gravity, or something else entirely, its explanation will likely reshape fundamental physics. Until then, dark energy remains what it has always been since its discovery. A name for a phenomenon we can measure, but not yet comprehend. If dark energy resists explanation, if it quietly shapes everything while remaining unknown, what does it mean to live inside such a universe? How do we situate ourselves in a cosmos driven by something we cannot see or name with confidence? Living inside a universe shaped by something we do not understand is not as unusual as it might sound. It feels unsettling when stated plainly, but uncertainty has always been part of humanity's relationship with the cosmos. What has changed is not the presence of the unknown, but its scale. Dark energy does not govern a corner of reality or an obscure phenomenon. It governs the future of everything quietly and persistently, without offering an explanation in return. And yet, daily life continues unchanged. Stars still rise and set. Planets still follow their paths. Time still moves forward in the familiar way it always has. Dark energy does not intrude on mornings or conversations or sleep. It does not tug at thoughts or rearrange routines. Its influence is so broad, so evenly spread, that it disappears completely at the scale of human experience. This contrast is one of the most striking aspects of the story. We live inside a universe whose long-term behavior is controlled by something we cannot see, cannot touch, and cannot define. Yet our immediate surroundings remain governed by forces we understand well enough to build lives around. Gravity still holds us to the Earth. Electromagnetism still binds matter. Chemistry still works. Biology still unfolds. The unknown sits above it all, shaping outcomes far beyond any horizon we can reach. This separation of scales allows both certainty and mystery to coexist. It allows science to function locally while admitting profound ignorance globally. It also allows human meaning to exist independently of cosmic explanation. There is a temptation to interpret dark energy as something ominous, simply because it is unknown and powerful. But power, in this case, does not mean dominance in the way we usually imagine it. Dark energy does not command events. It does not dictate outcomes moment by moment. It does not intervene. It sets conditions. It determines how space itself behaves over vast distances and long times, and from those conditions, everything else follows naturally. Galaxies drift apart. Horizons form. Isolation increases. But nothing is forced abruptly. There is no pressure to hurry. From the inside, from where we sit, the universe feels stable. This stability is important, because it highlights a subtle but often overlooked point. Knowing that the universe is driven by something unknown does not make it chaotic. On the contrary, dark energy appears remarkably steady. Its behaviour is simple, predictable, and consistent. The mystery lies not in what it does, but in why it exists at all. That distinction matters when thinking about what it means to live in such a universe. For most of human history, the unknown was associated with danger. Unseen forces were threats. Unexplained phenomena were signs of instability. But modern science has shown that many unknowns are not dangerous at all. They are simply unexplored. Dark energy has been present for billions of years. It did not prevent stars from forming. It did not stop galaxies from assembling. It did not interfere with the emergence of complexity. In fact, its gentleness may have helped create the conditions that allowed structure to persist rather than collapse. If dark energy had been stronger early on, the universe might have expanded too quickly for matter to gather. If it had been weaker or absent, gravity might have led to collapse or a very different cosmic history. The unknown, in this case, has been quietly permissive. This reframes how one might think about ignorance in science. Not knowing does not always imply instability. Sometimes it implies that the universe is operating within a narrow, stable range that we have not yet learned how to explain. Living inside such a universe means accepting that explanation lags behind description. We are very good at describing what happens. We can measure expansion rates, map cosmic structure, calculate trajectories, and predict outcomes billions of years into the future, all while lacking a fundamental explanation for the dominant driver behind those outcomes. This separation between prediction and understanding is uncomfortable, but it is not new. For centuries, gravity was used effectively without anyone knowing what it was. Newton described how gravity behaves, not what it is. Objects fell, orbits persisted, predictions were accurate, dictions. Explanation came much later, and even then only partially. Dark energy occupies a similar position now. We know how it behaves well enough to predict the universe's future under certain assumptions. We do not know what it is. Living with that gap requires a shift in expectation. It means allowing knowledge to be provisional, layered, and incomplete without treating it as fragile. The universe does not wait for us to understand it before behaving. There is also a quiet philosophical implication here. If the fate of everything is shaped by something fundamentally unknown, then certainty about ultimate outcomes is always conditional. Predictions depend on assumptions. Futures depend on parameters whose origins are unclear. This does not make predictions useless. It makes them honest. Science, at its best, does not claim final answers. It offers the best available explanations while remaining open to revision. Dark energy forces this humility into the foreground. It also challenges narratives that place humanity at the centre of cosmic meaning. The universe is not unfolding in response to observation or awareness. It is not shaped by intention. It is shaped by properties of space-time itself, indifferent to interpretation. And yet meaning still arises. Meaning arises locally, within systems where forces balance, where complexity can persist, where change unfolds at a pace compatible with experience. Dark energy does not erase this. It creates a background against which it happens. From this perspective, living inside a universe pushed by the unknown is not a source of despair. It is simply the condition of existence. Every era of human understanding has had its dominant unknown. Once it was the nature of the stars, then the structure of atoms, then the origin of time. Each unknown felt foundational at the time. Each eventually yielded, at least partially, to deeper understanding. Dark energy may follow the same path, or it may remain unresolved longer than any previous mystery, forcing a reconsideration of what explanation itself means. Either outcome fits within the larger pattern of scientific progress. There is also a psychological dimension worth noticing. Humans often seek closure. We prefer stories with clear causes and clear endings. Dark energy offers neither. It provides no clear origin story and no dramatic conclusion. The universe it shapes does not end with a bang or collapse neatly back into itself. It drifts toward increasing separation and quiet. This kind of ending is difficult to narrate because it lacks tension and resolution. It simply continues. But continuity, rather than finality, may be the more honest description of cosmic behaviour. Living inside such a universe encourages a different way of thinking about time and significance. If the universe continues expanding indefinitely, then no single moment is privileged as an ending. Meaning is not located at a conclusion, but within ongoing processes. Stars burn because they burn. Life unfolds because conditions allow it. Consciousness arises because complexity reaches certain thresholds. Dark energy does not interrupt these processes, it surrounds them. Another aspect of living with the unknown is recognizing the limits of perspective. We experience the universe from a particular vantage point, at a particular time, within a particular structure. From this position, dark energy appears as a smooth, uniform influence shaping expansion. From another vantage point, perhaps far in the future, the universe may look very different. Observers then may infer different histories, limited by what remains visible. The unknown shifts with context. This raises an interesting possibility. Dark energy may be fundamentally simple, but our access to its effects changes over time. What we can observe now may not be observable later. The window of understanding is not fixed. This gives present-day cosmology a certain urgency, not because answers must be rushed, but because opportunities are finite. Still, the fact that dark energy erases evidence of the universe's past does not erase the past itself. It simply limits access to it. Living inside such a universe means that knowledge is historically contingent. What can be known depends on when one asks. This does not diminish the value of knowledge, it contextualizes it. There is also a sense in which dark energy reframes humanity's place in the universe. We are not observers standing outside reality, watching it unfold. We are participants inside a process whose rules we are still uncovering. We measure expansion because we are embedded in it. We infer dark energy because we are carried along by the same space-time it influences. This embeddedness matters. It reminds us that understanding is always partial, always shaped by position. The unknown, in this sense, is not an external threat. It is part of the environment. Accepting this can feel uncomfortable, but it can also be stabilizing. It removes the expectation that everything must be explainable in human terms. The universe does not owe us clarity. It offers patterns, consistency, and opportunities for understanding, but it does not guarantee completion. Dark energy exemplifies this. It behaves consistently enough to be modelled, yet resists reduction to familiar categories. It forces science to operate at the edge of explanation, and that edge is where science has always grown. Living inside a universe pushed by the unknown also invites reflection on what questions matter most. If the ultimate driver of cosmic fate remains mysterious, does that diminish the importance of understanding smaller-scale processes? The answer, clearly, is no. Understanding stars, planets, life, and consciousness remains valuable regardless of whether the deepest cosmic parameter is explained. These domains operate according to principles that are accessible, testable, and meaningful within our experience. Dark energy does not negate them. In fact, the fact that such a mysterious influence allows these domains to exist at all may be seen as a quiet allowance rather than a threat. The universe is large enough to contain both mystery and familiarity. As the exploration of dark energy continues, new data will arrive, measurements will improve, constraints will tighten. Some possibilities will be ruled out, others may gain support. At some point, a deeper explanation may emerge, or it may not. Either way, living inside a universe pushed by the unknown does not mean living without understanding. It means living with layers of understanding, some complete, some provisional, some unresolved. This layered knowledge is not a weakness. It is a realistic portrait of how complex systems are understood. There is no final chapter where everything is explained and nothing remains uncertain. there is only continued refinement, and that refinement continues whether or not we watch it. Dark energy does not require belief. It does not require interpretation. It does what it does regardless of how it is named. The universe expands. That expansion accelerates. Structures drift apart. Horizons form. Within those conditions, stars shine. Planets orbit. Minds reflect. Living inside a universe pushed by the unknown means recognizing that meaning is not delivered from the outside. It is constructed locally, within constraints that are stable enough to allow continuity. The unknown sets the stage. It does not write the script. As this exploration settles, there is no need for a conclusion that feels final. The universe itself does not provide one. It continues, shaped by influences we measure and others we have yet to understand. Dark energy remains there, quiet, uniform, patient, and within that vast, gently expanding space, life continues to unfold moment by moment, asking questions not because answers are guaranteed, but because curiosity itself is one of the few things that expansion cannot dilute.